We often think we know our place in the universe, that our home galaxy is something we understand. But the truth is far more surprising and beautiful than most people realize. The Milky Way, which feels so vast and permanent to us, is actually just one ordinary spiral among trillions of others, many of which are so enormous they make our entire galaxy look like a small town next to a sprawling metropolis. Scientists have discovered galaxies with hundreds of times more stars than ours, galaxies that collide and merge in cosmic dances lasting billions of years, and vast cosmic cities where thousands of galaxies cluster together. Reality is far stranger and more magnificent than we typically imagine, and our understanding keeps shifting as we peer deeper into space. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. Looking up at the night sky, we find ourselves passengers on a cosmic vessel we call the Milky Way. This spiral collection of stars carries us through space at incredible speeds. Yet from our perspective, everything seems perfectly still. Our galaxy contains somewhere between 200 and 400 billion stars, each one a sun in its own right, many hosting their own families of planets. The Milky Way measures roughly 100,000 light-years from edge to edge. To put that in perspective, light from one side of our galaxy takes 100,000 years to reach the other side. We live about 26,000 light-years from the galactic center, nestled in what astronomers call the Orion Arm, a minor spiral branch that extends outward from the main structure. From our position inside this stellar metropolis, the galaxy appears as a faint band stretching across the night sky. Ancient civilizations saw this ghostly river of light and created stories to explain its presence. The Greeks called it the Milky Way, believing it was milk spilled from the breast of the goddess Hera. Other cultures saw it as a path for souls, or a cosmic serpent, or the backbone of the night itself. What we now know is that this pale streak represents our edge on view of the galactic disk. Imagine looking at a dinner plate from the side, the thin edge barely visible. That's our perspective on our own galaxy. We're embedded within it, like insects crawling along the surface of that plate, trying to understand the full scope of our surroundings. The Milky Way rotates once every 225 million years. This means that since Earth formed, our solar system has completed only about 20 trips around the galactic center. Dinosaurs lived and died during just one of these cosmic years. Human civilization occupies merely a tiny fraction of a single galactic rotation. Our galaxy belongs to a small cluster of galaxies called the local group. This neighborhood contains about 80 galaxies in total, though most are small, dim collections of stars called dwarf galaxies. The local group spans about 10 million light-years across, making the Milky Way seem quite modest by comparison. The largest member of our local neighborhood is the Andromeda Galaxy, also known as M31. Andromeda contains roughly 1 trillion stars, more than twice the stellar population of the Milky Way. It stretches about 220,000 light-years across, making it significantly larger than our home galaxy. From Earth, Andromeda appears as a faint smudge in the constellation of the same name, yet it represents an entire world of worlds, each star potentially hosting planets, moons, and perhaps even life. In about 4.5 billion years, the Milky Way and Andromeda will collide. This sounds catastrophic, but galactic collisions unfold over hundreds of millions of years. The stars within each galaxy are separated by such vast distances that very few actual stellar collisions will occur. Instead, the two galaxies will dance around each other, their spiral arms becoming distorted, their gas clouds merging to form new generations of stars. The combined galaxy, which astronomers playfully call Milkomeda, will eventually settle into an elliptical shape. By that time, our sun will have exhausted its fuel and expanded into a red giant, making the merger somewhat irrelevant for Earth's future. Still, there's something profound about knowing our galaxy has an appointment with its neighbor, billions of years in the future. Beyond our local group lie galaxy clusters containing hundreds or thousands of galaxies. The nearest major cluster, called the Virgo cluster, contains over 1,000 galaxies and sits about 54 million light-years away. At the heart of this cluster sits M87, an elliptical galaxy that dwarfs both the Milky Way and Andromeda. M87 contains several trillion stars and measures about 120,000 light-years across at its widest point. But what makes M87 truly remarkable is its supermassive black hole, which weighs as much as 6.5 billion suns. This black hole became famous as the first to be directly imaged by the Event Horizon Telescope, appearing as a bright ring of glowing gas surrounding a dark shadow. The black hole at the center of M87 powers enormous jets of particles that shoot out into space at nearly the speed of light. These jets extend for thousands of light years, creating structures larger than many entire galaxies. The energy required to maintain these jets comes from matter falling into the black hole, releasing tremendous amounts of radiation as it spirals toward the point of no return. Our own galaxy hosts a supermassive black hole called Sagittarius A star, which weighs about 4 million times more than our Sun. While impressive by earthly standards, this makes our galactic center seem almost quaint compared to the monster lurking in M87. The relationship between galaxies and their central black holes remains one of the most fascinating areas of modern astronomy. Galaxy formation represents one of the universe's most complex processes. Shortly after the Big Bang, tiny fluctuations in the density of matter began to grow under the influence of gravity. Dark matter, which outweighs ordinary matter by a factor of 5 to 1, formed the scaffolding upon which galaxies would eventually build themselves. Over hundreds of millions of years, gas fell into these dark matter wells, heating up and beginning to form the first stars. These early stars were massive, short-lived, and contained only hydrogen and helium. When they exploded as supernovae, they scattered heavier elements throughout space, providing the raw materials for planets, asteroids, and eventually, life itself. The Milky Way likely formed through a combination of gradual gas accretion and the merger of smaller galaxies. Evidence for this violent past can be found in the stellar streams that wrap around our galaxy, the stretched-out remains of dwarf galaxies that wandered too close and were torn apart by tidal forces. Some of the most spectacular galaxies in the universe are the giant ellipticals found at the centers of massive galaxy clusters. These cosmic cities can contain up to 100 trillion stars, making them among the most massive single objects in the universe. They formed through the merger of hundreds of smaller galaxies over billions of years, growing like cosmic snowballs, rolling through space. IC 1101, located about 1 billion light-years away, ranks among the largest known galaxies. It measures roughly 6 million light-years across and contains an estimated 100 trillion stars. To put this in perspective, you could fit more than 50 Milky Way galaxies across its diameter. The central black hole in IC 1101 likely weighs tens of billions of times more than our Sun. These monster galaxies challenge our understanding of how structures grow in the universe. They represent the end point of galactic evolution, cosmic retirement homes where star formation has largely ceased. Their stellar populations are old and red, having long ago exhausted the gas supplies needed to birth new stars. The space between galaxies is not empty, but filled with thin wisps of gas and mysterious dark matter. Galaxy clusters themselves are connected by filaments of matter that stretch across hundreds of millions of light-years. This cosmic web represents the largest scale structure in the universe, with galaxies strung along its threads like dewdrops on a spider's web. Within galaxy clusters, the space between galaxies glows with X-ray radiation from gas heated to millions of degrees. This intergalactic medium contains as much mass as all the galaxies combined, yet remains largely invisible to optical telescopes. Only by observing in X-rays can astronomers map this hidden component of cosmic architecture. The fact that we live in a medium-sized galaxy in a small group on the outskirts of a modest cluster might seem to diminish our cosmic significance. Yet this location may have been crucial for the development of complex life. Larger galaxies experience more frequent collisions and supernovae, creating environments hostile to stable planetary systems. Our position in the Milky Way's suburbs keeps us away from the chaotic galactic center, while providing enough heavy elements created by previous generations of stars to build rocky planets, we orbit in what astronomers call the galactic habitable zone, where conditions remain stable enough for life to evolve over billions of years. The study of galaxies reveals something profound about the nature of existence itself. These island universes, each containing billions or trillions of stars, represent laboratories where the elements of life are forged and distributed throughout space. Every atom in our bodies, save hydrogen, was created in the nuclear furnaces of stars that lived and died before our sun was born. In this cosmic perspective, we are not separate from the universe but intimately connected to it. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were manufactured in stellar cores and scattered by supernovae across the galaxy. We are quite literally made of star stuff, temporary arrangements of atoms that have been cycling through the galaxy for billions of years. This connection extends beyond our physical composition to our very existence. The Milky Way's gentle rotation, its stable structure, its location in a quiet cosmic neighborhood, all contributed to creating conditions where planets could form, where life could emerge, where intelligence could develop to contemplate its own origins. Perhaps our galaxy's ordinariness is actually its greatest gift. In a universe of extremes, where some galaxies are too small to sustain complex chemistry and others too large to maintain stability, we find ourselves in a cosmic Goldilocks zone, where everything is just right for the long, slow process of evolution to unfold. From our place deep inside this galaxy, we can never really step back and see what we're part of. The Milky Way surrounds us completely, like we're living inside a massive snow globe. Every direction we look, there are thousands of light years of stars between us and whatever lies beyond them. You know how you can live in a city your whole life, but never really see its shape because you're always walking at street level? That's exactly what it's like being inside our galaxy. We can sense the structure around us. We can feel the busy center, the quieter edges, but we'll never get that bird's eye view. For decades, astronomers have been putting together this cosmic puzzle piece by piece. They use radio waves, infrared light, all kinds of data to map what we can't actually see. And what emerges from all that detective work is a spiral. Not perfect, mind you, more like something alive, with arms that twist and bend in slightly uneven ways. The galaxy has 4 main arms, plus smaller branches and bridges connecting them. Each arm is packed with gas clouds, dust, and clusters of brand new stars. Our sun, and therefore all of us, sits in a small spur tucked between 2 of the major arms. We're in the cosmic suburbs, you might say, far from all the action at the center. If you could somehow float above the entire Milky Way, it would stretch about 100,000 light years from edge to edge. Now, 1 light year is roughly 9 trillion kilometers. So we're talking about a quintillion kilometers across. That's a number you can say out loud, but your brain just can't really grasp what it means. The whole thing rotates too, taking about 230 million years to complete 1 full turn. Think about this. Since the first dinosaurs appeared on Earth, our sun has only made it around the galaxy once.
Right now, as you're listening to this, we're cruising through space at about 220 kilometers per second, and yet everything around us feels perfectly still.
At the heart of our galaxy lies something we can't see directly. Dense clouds of dust block our view, but hidden in that darkness sits Sagittarius A star, a super-massive black hole. This thing weighs about 4 million times more than our sun. But it's not some cosmic vacuum cleaner sucking everything up. It's actually pretty calm, just quietly munching on the occasional gas cloud that wanders too close. Around this invisible giant, stars race in tight orbits at incredible speeds. Some complete their loops in just a few years. These racing stars have helped scientists figure out exactly how massive the black hole is. It's like the gravitational anchor that holds everything together. Surrounding the center is what astronomers call the bulge. It's a thick, crowded region full of older stars that glow with golden light. Beyond that, the spiral arms sweep outward in graceful curves. Here's something fascinating about those arms. They're not fixed structures like the spokes of a wheel. They're more like traffic patterns in space. Regions where stars and gas bunch up, because of density waves moving through the galaxy's disk. New stars form in these waves, light them up brilliantly, then drift away as the pattern moves on. The spiral arms are like rivers that never stop flowing. Always changing, always in motion, though that motion happens over millions of years. It makes you wonder about the nature of permanence, doesn't it? Even the most solid-looking structures in the universe are constantly shifting. If you imagine the Milky Way as a glowing disk, there's also a faint spherical halo wrapped around the whole thing. This halo contains some of the oldest stars in the galaxy, along with mysterious globular clusters. But most of the halo's mass comes from something we can't see at all: dark matter. This invisible dark matter makes up most of our galaxy's mass. Without it, the stars on the outer edges would be spinning too fast. They'd just fly off into the void. Dark matter acts like invisible scaffolding, holding the entire structure together. It's there, shaping everything, but we can only detect it through its gravitational effects. From our position about halfway between the center and the edge, the night sky looks rich and crowded. If you've ever been somewhere truly dark, away from city lights, you've probably seen that faint band of white light crossing the sky. That's our galaxy seen from the inside. You're looking at the combined glow of hundreds of millions of distant stars. Even then, you're only seeing a tiny slice of the whole thing. Dust blocks your view after just a few thousand light years. If you could see through all that dust, the Milky Way would wrap around the entire sky like a soft, glowing ring. It's humbling to realize our solar system is just one among hundreds of billions in this vast structure. Current estimates suggest there might be anywhere from 100 to 400 billion stars in our galaxy, and probably even more planets, perhaps trillions of them. Among all those worlds, billions could be roughly Earth-sized, orbiting at just the right distance where liquid water might exist. Somewhere out there, other planets may have their own versions of night skies, their own quiet observers wondering if they're alone in the universe. In that sense, our galaxy isn't just a collection of stars and gas. It's potentially a cradle for countless forms of life we've never imagined. Each star system could harbor its own stories, its own mysteries. When astronomers study the Milky Way's light and compare it to other galaxies, they find we're pretty typical. Not especially large, not particularly small. Our rotation speed, star count, diameter, they all fall right in the middle of the range for spiral galaxies. There's something oddly comforting about that ordinariness. It means our cosmic home is stable and balanced. Some galaxies burn through their fuel too quickly, forming stars at a furious pace until they exhaust themselves. Others are quiet and dim, their star-forming days long behind them. The Milky Way sits perfectly in between, creating a few new stars every year, just enough to keep things lively and glowing, but not so many that it tears itself apart. It's like finding out you live in the most stable neighborhood in the universe. Our galaxy doesn't exist in isolation, though. It's surrounded by smaller companion galaxies that orbit around us like satellites. The two most visible ones are called the Large and Small Magellan Counts. If you're ever in the southern hemisphere, you can see them as hazy patches of light in the night sky. These smaller galaxies are slowly being torn apart by the Milky Way's gravity. They leave behind long trails of gas that wrap around us like invisible ribbons. Eventually, they'll probably merge with us completely, adding their stars to our collection. This slow gathering of smaller galaxies has been happening throughout the Milky Way's entire history. It's one of the main ways galaxies grow, not just by making new stars, but by absorbing their neighbors. It's a gradual process that spans billions of years. If you could somehow watch our galaxy's entire life story in fast forward, you'd see something truly dynamic. Streams of gas flowing inward to feed new generations of stars, clusters of stars moving like schools of fish, following gravitational currents. Tiny galaxies falling in, stretching and blending until they disappear entirely. The spiral pattern would flicker and shift over time, and through it all, the galaxy would keep spinning in that slow, steady rotation that's been going on for more than 10 billion years. It's simultaneously ancient and alive, constantly changing but somehow never losing its essential character. What strikes me most about all this is how it challenges our everyday sense of what's permanent and what's temporary. The Milky Way feels eternal from our perspective, but it's actually in constant flux. Stars are born, live their lives, and die. Gas flows in complex patterns. The entire structure evolves over cosmic timescales. Yet somehow, through all that change, the galaxy maintains its identity. Its spiral arms keep forming, its rotation continues, its overall structure persists. It makes you think about what it means for something to be the same thing over time, when every part of it is constantly being replaced or rearranged. 30 galaxies drift together through space, bound by invisible threads of gravity. This is our cosmic neighborhood, what astronomers call the local group. The Milky Way belongs here, alongside Andromeda, its massive companion. Together they anchor this small cluster, while dozens of smaller galaxies fill the space between them. Some of these neighboring galaxies shine bright enough for backyard telescopes to capture. Others hide so deep in darkness that only the most sensitive instruments can detect their faint glow. Each carries its own history, its own collection of stars, born and died over billions of years. When you look up at night, every star you see belongs to our galaxy's flat disk. But zoom out far enough, and this disk becomes just one tiny point in something much larger. Cosmic filaments stretch across the universe like a vast web, made of dark matter and gas. Galaxies cluster along these threads, creating a structure that spans distances our minds struggle to grasp. The Milky Way sits at one intersection of this web, glowing quietly among countless others. We're embedded so deep inside it that studying our own galaxy becomes surprisingly difficult. Clouds of dust block our view in visible light, creating cosmic fog that hides much of what we want to see. Radio waves slip through this dust like whispers through a crowd. Radio telescopes map hydrogen gas as it traces the spiral arms, revealing the galaxy's elegant structure. Infrared light penetrates deeper, showing us stars hidden in the galactic center. X-rays illuminate the most violent regions, where black holes devour matter and neutron stars spin at impossible speeds. Layer these different wavelengths together, and the Milky Way comes alive. What seemed static reveals itself as dynamic, pulsing with energy and motion. Activity happens everywhere, from the quiet birth of stars to the explosive deaths that scatter elements across space. The oldest residents of our galaxy live in globular clusters, ancient cities of stars that formed over 12 billion years ago. These stellar elders witnessed the galaxy's youth, when it was still assembling itself from smaller pieces in the early universe. They watched as gas gradually settled into the flat disk we see today. Star formation became a rhythm, a cosmic heartbeat that continues now. Hydrogen and helium collapse under their own weight, igniting nuclear fires that burn for millions or billions of years. The most massive stars live fast and die spectacularly, exploding as supernovas that forge heavy elements in their final moments. Carbon, oxygen, iron, and dozens of other elements scatter into space, mixing with fresh hydrogen to create new stars and planets. This cycle connects everything in ways that feel almost mystical. The calcium strengthening your bones formed inside a star that died before our solar system existed. The iron carrying oxygen through your blood came from stellar explosions billions of years ago. We are not separate from the galaxy. We are made of it, assembled from its recycled materials, products of its long history of stellar death and rebirth. Every element heavier than hydrogen was forged in stellar cores or explosive collisions, making us literal children of the stars. Modern space missions have begun mapping our cosmic home with unprecedented precision. The Gaia spacecraft has measured positions and movements for over 1 billion stars, creating a three-dimensional portrait of galactic structure. Scientists can now trace how stars move through the galaxy, where they formed, how they migrate over time. This data reveals the Milky Way as a living system, breathing slowly as gravity shapes its spiral arms. Stars don't stay in fixed positions. They orbit the galactic center, on journeys that take hundreds of millions of years, rising and falling through the disk like carousel horses. Our solar system rides along one of these arms, about halfway out from the center. Astronomers call our location the Orion Arm, a relatively quiet suburban region of the galaxy. We're not too close to the crowded core, where gravitational chaos might disrupt planetary orbits. Not too far out in the sparse outer regions, where heavy elements become scarce. This location matters for life's development. Closer to the center, the night sky would blaze with millions of nearby stars, but radiation and gravitational disturbances would make stable planetary systems difficult. Too far out, and the elements needed for rocky planets and complex chemistry become rare. Our cosmic address sits in what some call the galactic habitable zone, where conditions favor the long, stable evolution that complex life seems to require. The nights stay dark enough for delicate biological processes to unfold without constant stellar interference. There's something profound about living inside a spiral galaxy, participating in its slow rotation, without really feeling the motion. The spiral pattern itself moves like a wave, with stars entering and leaving the arms over millions of years. Density waves compress gas and trigger star formation, lighting up the arms before the stars drift away again. This creates the illusion of permanent structure when everything is actually in flux. The spiral arms we see today are not the same collection of stars that formed them millions of years ago. It's like a traffic jam that maintains its shape, even as individual cars move through it. From our embedded perspective, we can only see fragments of this grand design. But those fragments tell a story of emergence, of how simple physical laws create complex, beautiful structures over vast scales of time and space. Gravity pulls, gas flows, stars ignite and die, yet somehow order persists through the chaos. The Milky Way demonstrates how systems can be both ancient and dynamic, massive yet delicate, violent yet nurturing. It has existed for most of the universe's history, but continues evolving, changing, creating new stars and planets, where life might someday take hold and look up at its own cosmic home with wonder. Looking out beyond our cosmic neighborhood, you realize that distance changes everything. What seems endless from the inside suddenly becomes just one piece of a much larger puzzle. The universe holds more galaxies than there are grains of sand on all the beaches of Earth, maybe even more than that. When astronomers first pointed their most powerful telescopes at what looked like completely empty patches of sky, they discovered something that shifted our entire understanding of existence. They picked a tiny spot, no bigger than what a grain of sand would look like if you held it at arm's length, and took a very long exposure photograph. What came back was breathtaking. Thousands upon thousands of galaxies, each one containing hundreds of billions of stars, all packed into that minuscule slice of apparent nothingness. This discovery led to one of the most mind-bending numbers in all of science. The observable universe likely contains around 2 trillion galaxies. That's 2,000 billion separate cosmic cities, each one a vast collection of stars, gas, dust, and invisible dark matter, all dancing around a central point of gravity. The word galaxy comes from ancient Greek, meaning milky, named after that pale streak of light our ancestors saw painted across the night sky. For most of human history, people believed that faint band was everything that existed. The entire cosmos, they thought, was contained within that ghostly arc above their heads. Even as telescopes got better, scientists still assumed all those fuzzy patches of light they could see were just parts of our own galactic neighborhood. It took until the 1920s for someone to prove otherwise. An astronomer named Edwin Hubble studied a mysterious cloudy object in the constellation Andromeda, identifying individual variable stars within it and calculating their distances. His measurements revealed something extraordinary. This wasn't part of our galaxy at all. It was another galaxy entirely, a completely separate island universe floating in the cosmic ocean. That single discovery expanded our known cosmos from one galaxy to countless millions in an instant. Suddenly, we weren't alone in the universe. We were just one small community in an infinite city of communities. The idea of galaxies as islands remains one of the most useful ways to picture our universe. Each one is held together by its own gravity, surrounded by the dark emptiness of space, separated from its neighbors by truly staggering gulfs of nothingness. Our nearest major galactic neighbor, Andromeda, sits about 2.5 million light-years away. The light reaching us from Andromeda tonight began its journey when early humans were still chipping stone tools. Between here and there lies almost perfect emptiness. A thin whisper of hydrogen gas, a few scattered rogue stars, and vast amounts of dark matter that we can't even see. These distances are so immense that even traveling at light speed, the fastest possible velocity in the universe, a message from one galaxy to another would take millions of years to deliver. Yet despite these enormous separations, galaxies don't remain isolated forever. Gravity never stops working, even across these cosmic distances. It's incredibly patient, pulling galaxies toward each other over billions of years. Small groups form first, then larger clusters, then enormous superclusters containing thousands of galaxies, all bound together in vast webs that stretch across the entire observable universe. If you could somehow drift through space, passing these cosmic islands one by one, you'd encounter an extraordinary variety of forms and personalities. Some galaxies are smooth and nearly spherical, with their stars packed tightly toward the center, like a cosmic snowball. Others spread out flat and delicate, forming the classic spiral shapes you see in astronomy textbooks, with graceful arms sweeping outward from a bright central bulge. Many galaxies are irregular and chaotic, their shapes twisted and distorted by ancient collisions with their neighbors. Some blaze with the fierce light of newly forming stars, their gas clouds glowing brilliant blue and white from intense ultraviolet radiation. Others appear old and red, having exhausted their star-forming materials billions of years ago, now populated only by ancient stellar residents slowly fading away. Each galaxy represents its own unique ecosystem of gravity, light, and time. They're cosmic laboratories where the fundamental forces of nature play out their long, slow experiments across billions of years. In a sense, every galaxy is a different answer to the same basic question: what happens when you gather enough matter together in one place and let gravity and physics do their work for cosmically long periods of time? This vast population of galaxies fills the universe in every direction we look. Point a sensitive telescope anywhere in the sky, peer deep enough into space and time, and you'll see the same sight repeated endlessly. Tiny flecks of light scattered across the darkness, each one representing an entire world of stars and possibilities, each one carrying the light of billions of suns across the emptiness to reach us here. The universe organizes itself in ways that might surprise you. We live inside the Milky Way, which sits comfortably in what astronomers call the local group. This local neighborhood, in turn, belongs to something much grander, the Virgo supercluster. But even that massive structure is just one piece of an even more impressive puzzle. When you zoom out far enough, the cosmos reveals its true architecture. Galaxies don't just float around randomly in space. They follow invisible highways, stretching across billions of light years like cosmic filaments. These threads of matter connect galaxy clusters together, forming what scientists call the cosmic web. It's almost as if the universe has veins, carrying galaxies instead of blood. Between these filaments, something equally fascinating exists. Vast empty regions called cosmic voids stretch for hundreds of millions of light years. Almost no galaxies live in these dark territories. They're like enormous bubbles in the cosmic foam, spaces where matter simply decided not to gather. Picture the entire universe as a kitchen sponge. The solid parts represent where galaxies cluster together along walls and filaments. The holes represent the voids. This spongy structure emerged from the tiniest fluctuations right after the Big Bang. Gravity spent billions of years amplifying these small density differences, stretching them into the grand pattern we see today. Every galaxy owes its existence to this ancient blueprint. That includes our own Milky Way, with its graceful spiral arms. It includes distant elliptical galaxies, smooth and featureless. Even the smallest dwarf galaxies, trace their origins back to those primordial ripples in spacetime. Mapping this cosmic architecture requires incredible dedication. Astronomers use light from millions of galaxies to trace out the universe's skeleton. Each point on their maps represents not a single star, but an entire galaxy containing hundreds of billions of stars. The scale becomes almost impossible to grasp. Galaxies themselves lead surprisingly dynamic lives. They form from collapsing clouds of gas and dark matter. They grow by consuming smaller neighbors. When two galaxies collide, they dance around each other for millions of years before finally merging. These cosmic crashes can trigger massive bursts of star formation, lighting up the galaxy like a celestial fireworks display. Some galaxies burn bright and fast, quickly exhausting their gas supplies. Others pace themselves, forming new stars steadily for billions of years. Eventually, many galaxies fade as their fuel runs out. They become retirement homes for aging stars. Elliptical collections of ancient suns, with no new generations being born. The variety among galaxies is truly staggering. The most numerous are dwarf galaxies, containing just a few million stars. Their irregular shapes make them look almost chaotic compared to their larger cousins. They orbit around giant galaxies like cosmic satellites, vulnerable to gravitational bullying from their massive neighbors. At the other extreme, the largest elliptical galaxies contain trillions of stars. Their diameters can exceed 1 million light-years. To put that in perspective, light itself takes over 1 million years to cross from one side to the other. These galactic monsters often sit at the centers of galaxy clusters, having grown fat by consuming everything around them. Between these extremes live the graceful spirals like our Milky Way and Andromeda. They maintain their elegant disk shapes, while actively forming new stars. Their spiral arms sweep through space like cosmic pinwheels, lighting up with the blue glow of young, hot stars. If you could somehow float in the empty space between galaxy clusters, the darkness would seem overwhelming. Your eyes would detect almost nothing. But appearances can deceive. If you could see all wavelengths of light, you'd discover that space itself glows faintly. This cosmic background light comes from the combined glow of billions of galaxies, stretched and softened by the universe's expansion. In every direction you might look, that faint glow reminds you that the universe is populated. There's no direction that doesn't eventually lead to another island of stars. Even the darkest patches of sky contain distant galaxies, waiting to be discovered by more powerful telescopes. If it var descend, the darkest patches of sky contain distant galaxies. Galaxies serve as the universe's organizational system for matter. Without them, gas would remain too thinly spread for star formation. Gravity acts as a cosmic shepherd, gathering material together until it becomes dense enough to ignite nuclear fusion. Once a galaxy forms, it creates its own sustainable ecosystem. Dying stars return enriched material to their galaxy's interstellar medium. This recycled gas, now containing heavier elements forged in stellar cores, becomes the raw material for new stars and planets. Over cosmic time, galaxies gradually become more chemically rich. This chemical evolution makes possible the formation of rocky planets and, potentially, life itself. Recent discoveries have revealed galaxies that challenge our expectations. Ultra-diffuse galaxies spread themselves so thin that they're nearly invisible. These cosmic ghosts have the size of the Milky Way, but contain only a tiny fraction of its stars. Finding them requires extremely long exposures and careful analysis. On the opposite end of the spectrum, some galaxies pack enormous amounts of matter into surprisingly small spaces. They appear almost star-like through telescopes, hiding their true galactic nature. Many of these compact galaxies host supermassive black holes at their centers. When material falls into these black holes, it creates brilliant quasars that can outshine entire normal galaxies. The feeding of these central black holes creates some of the most energetic phenomena in the universe. Jets of material shoot out at nearly the speed of light, extending far beyond the galaxy itself. These cosmic lighthouses can be detected across billions of light years, serving as beacons from the early universe. Understanding galaxies means appreciating them not as isolated islands, but as connected parts of a living cosmic web. While the universe expands on the largest scales, gravity still binds galaxies together within clusters. They orbit each other, exchange material, and occasionally merge in spectacular cosmic collisions that reshape their structures completely. Every galaxy carries within it the scars and stories of cosmic violence that most people never really think about. When two galaxies meet in the depths of space, it's not the gentle merger you might imagine from those smooth animations. These encounters stretch and warp entire stellar neighborhoods, pulling billions of suns into long sweeping arcs that trail behind like cosmic hair. Stars get flung out into the darkness, suddenly homeless, drifting between galaxies with no clear destination. What we see as peaceful pinwheels of light from Earth are actually the survivors of countless collisions, their spiral arms constantly being rewound by gravity's patient hands. The strangest part about looking at galaxies is that we're essentially time travelers without a machine. Every photon that hits our telescopes left its home galaxy millions, sometimes billions of years ago. That means the farther out we look, the younger everything appears. It's like watching a movie played backwards. Where the universe gets smaller and more chaotic, the deeper we peer into space. Those distant, fuzzy patches of light that barely register on our instruments, they're showing us galaxies as they were when they were still figuring out how to be galaxies. Small, messy, still gathering themselves together from the cosmic debris left over from the beginning of everything. Closer to home, we have galaxies like Andromeda, which represent the universe's middle age, when things had settled into more familiar patterns. These mature systems give us a glimpse of what cosmic adolescence looks like after the wild early years but before the slow fade that comes with extreme old age. By comparing these different snapshots, scientists can piece together the biography of the cosmos, watching how simple clumps of matter eventually organized themselves into the magnificent structures we see today. There's something almost comforting about realizing that the universe's enormous scale isn't really about us being small. It's just about time having had so long to work. Gravity moves slowly, light travels at a fixed speed, and when you give these forces billions of years to operate, big things naturally emerge. Our galaxy stretches across 100,000 light years, not because the universe is trying to make us feel insignificant, but simply because that's what happens when matter has 13 billion years to sort itself out under the influence of fundamental forces. The hydrogen atoms floating in galaxies billions of light years away are identical to the hydrogen atoms in your own body. The same physical laws that govern how stars form in the most distant observable galaxies also determine how planets coalesce around our own sun. In this sense, the universe reveals itself as a kind of vast democracy of matter, where the same basic ingredients and rules apply everywhere. Distance becomes less important when you realize that every galaxy, no matter how remote, is fundamentally made of the same stuff and follows the same cosmic cook. If you could somehow travel beyond our local neighborhood of galaxies, you'd eventually reach something called the Virgo cluster, where over 1,000 galaxies congregate like a cosmic city. The largest residents are ancient elliptical galaxies, massive and settled, occupying the prime real estate at the cluster's center. Around them, smaller spiral galaxies dance and orbit like satellites, creating a hierarchy that mirrors patterns we see everywhere in nature, from solar systems to social structures. These clusters themselves are just the beginning of an even grander organization. They link together along invisible highways of dark matter, forming filaments that stretch across hundreds of millions of light years. If you could step back far enough to see the entire observable universe at once, it would look like an enormous spiderweb made of light, with galaxies strung along the threads like dewdrops. Where these cosmic highways intersect, you find the richest galaxy clusters. Where they thin out, vast voids open up, regions so empty that crossing them would take longer than complex life has existed on Earth. These voids aren't just empty space though, they're essential parts of the cosmic ecosystem. Matter flows along gravitational gradients from the empty regions toward the more crowded filaments, feeding the ongoing process of galaxy formation and evolution. The universe constantly rearranges itself on these enormous scales, though so slowly that entire civilizations could rise and fall without noticing any change. From this cosmic perspective, our Milky Way becomes just one ordinary spiral among hundreds of billions, its light indistinguishable from countless others when viewed from sufficient distance. Yet from our position inside it, it remains completely unique, the only galaxy we'll ever know intimately. This duality runs throughout astronomy, how everything appears both utterly common and entirely special, depending on your point of view. At the hearts of the largest galaxy clusters sit the true giants of the universe, elliptical galaxies so massive they contain 10 times more stars than our entire Milky Way. These cosmic titans have grown fat by consuming smaller galaxies over billions of years, becoming the dominant lights visible across vast distances. They represent what happens when gravity has unlimited time and material to work with, creating structures so large they challenge our ability to comprehend them. Compared to these monsters, our own galaxy appears almost modest, a middle-sized spiral, living a quiet life in a relatively calm corner of the universe. When we gaze upward on a clear night, something deep inside us wants to count the lights we see. This urge to quantify the infinite feels as old as humanity itself. Our ancestors scratched tallies into cave walls, tracking seasons and cycles. There's comfort in numbers, a way to wrap our minds around things that seem too big to understand. The stars you can see with your naked eyes, maybe a few thousand on the darkest nights, all belong to our home galaxy. Not a single one of those twinkling points is actually another galaxy. The nearest major galaxy, Andromeda, appears as just a faint smudge if you know exactly where to look. Everything else lies far beyond what our eyes can detect. It wasn't until we built telescopes and learned to capture light over long exposures that we discovered the true nature of our cosmic neighborhood. The night sky isn't just sprinkled with a handful of distant lights. It's absolutely packed with galaxies, layer upon layer, stretching back through space and time. When astronomers count galaxies, they focus on what we call the observable universe. This represents everything from which light has had enough time to reach us since the cosmic expansion began. The edge of this observable sphere sits roughly 46 billion light-years away. That means the most distant light we can see has been traveling toward us for nearly the entire 13.8 billion-year history of the cosmos. We sit inside this enormous bubble, not because Earth occupies some special central position, but simply because we can only see as far as light has managed to travel in every direction. Within this sphere, current estimates suggest that there are perhaps 2 trillion galaxies. That number has grown over time as our instruments have improved. Earlier counts put the figure closer to 1 or 200 billion, but as telescopes became more sensitive, astronomers began detecting countless small, faint galaxies that had previously gone unnoticed. These dim dwarf systems dominate the cosmic census. The massive, spectacular galaxies that capture our imagination are actually quite rare, like bright landmarks scattered among crowds of smaller neighbors. To reach that 2 trillion figure, scientists combined data from deep space surveys with computer models of how galaxies change over billions of years. What they discovered was fascinating. Early in cosmic history, there were far more small galaxies than we see today. Over immense stretches of time, gravity has pulled many of these together, merging them into larger systems. So when we talk about counting galaxies, we're really asking about a specific moment in time. In the distant past, there were more. In the far future, there will likely be fewer as cosmic evolution continues its slow work of gathering and combining these island universes. Counting galaxies is essentially counting ancient light. Each photon, captured by our telescopes, has been racing through space for millions or billions of years. The deeper we peer into space, the further back in time we see. A single deep field image contains galaxies from many different eras all mixed together. Some appear nearby and mature, others look young and irregular, still forming their first generation of stars. Every point of light represents a window into a different chapter of cosmic history. It's like flipping through a photo album that stretches back to the very beginning of time itself. Our ability to detect these faint, distant galaxies depends entirely on how sensitive our instruments are. The famous Hubble Deep Field image from the 19s revealed about 3,000 galaxies in a patch of sky no wider than a grain of sand held at arm's length. Later observations pushed that count even higher, in the same tiny region. From such small samples, astronomers extrapolate to estimate what fills the entire sky. This approach works because the universe displays remarkable uniformity on large scales. The same basic distribution of galaxies appears no matter which direction we look. There's something almost philosophical about this cosmic consistency, this suggestion that the universe maintains the same character everywhere. But galaxies aren't just scattered randomly through space. They form an intricate cosmic web of clusters and filaments, with vast empty regions called voids between them. Counting requires accounting for this structure, for the way galaxies gather in dense neighborhoods and thin out in sparse areas. Scientists use statistical methods to correct for these variations, building a picture of average galaxy density across the cosmos. That density works out to roughly 1 galaxy per 10 million light-years. It sounds incredibly sparse when you put it that way, but when you multiply by the sheer vastness of observable space, the numbers become staggering. Perhaps there's something humbling about these counts that stretch beyond easy comprehension. Each galaxy contains billions or trillions of stars. Many of those stars likely host planets. The mathematics of possibility becomes almost overwhelming when you start multiplying these scales together. And yet, we keep counting, driven by that same impulse that made our ancestors mark phases of the moon. There's something deeply human about wanting to measure the immeasurable, to put boundaries around the boundless. In a way, every galaxy count is also a count of cosmic time itself, a tally of all the light that has managed to cross the universe and find its way to our small corner of existence. Modern astronomy has reached a point where we can actually estimate how many galaxies exist in our observable universe, which speaks volumes about how far our scientific methods have come. Every time astronomers point their telescopes toward the cosmos, they're gathering data that builds into something much larger than just pretty pictures. Redshift is one of those elegant discoveries that transforms our understanding completely. When light from distant galaxies travels through expanding space, it gets stretched, making the light appear redder than it originally was. The fascinating thing is, scientists can use this stretching effect like a cosmic measuring tape. The redder a galaxy's light appears, the farther away it sits from us, and the longer that light has been traveling through space. This creates an interesting situation, where looking farther into space actually means looking backward in time. Those distant red-shifted galaxies are showing us what they looked like billions of years ago, when their light first began its journey toward Earth. Astronomers use these redshift measurements to build three-dimensional maps of the universe, plotting where galaxies exist across both space and time. The process of counting galaxies becomes something like counting moments in cosmic history itself. Each galaxy represents not just a collection of stars, but a specific era in the universe's development. When we map their positions and distances, we're essentially creating a timeline of how structure formed after the Big Bang. Our current best estimates suggest there are roughly 2 trillion galaxies within the observable universe, though this number comes with important caveats. Many galaxies remain hidden from our view, either because they're too faint for current instruments to detect, or because dust clouds block their light from reaching us. The James Webb Space Telescope has already started revealing galaxies that previous instruments couldn't see, particularly those ancient systems that formed during the universe's first few 100 million years. These early galaxies appear quite different from what we see today, often smaller and more irregular in shape. What's particularly intriguing is that the total number of galaxies may have actually decreased over cosmic time. In the early universe, space was crowded with small, chaotic galaxy systems. Over billions of years, many of these merged together through gravitational attraction, creating fewer but larger, more organized structures. This evolutionary process raises questions about what we're really counting when we talk about galaxies. The number 2 trillion represents a snapshot of our current cosmic era, but the universe's galaxy population has been constantly changing through mergers and interactions. Numbers this large challenge our normal ways of thinking about quantity. 2 trillion becomes almost meaningless as a concrete concept. You could express the total number of stars in the observable universe as roughly 7,000 million billion, but even that doesn't make the scale feel more comprehensible. Perhaps it's more useful to think about galaxy density rather than total numbers. If you point a telescope at any patch of seemingly empty sky and look deep enough, you'll find it packed with entire galaxy systems. This holds true for every direction you might look, which suggests that empty space is essentially an illusion created by the limitations of our instruments. Galaxies function almost like pixels in a cosmic image, each one representing a cluster of potentially billions of stars. When astronomers count them, they're measuring how matter organized itself after the Big Bang, how gravity shaped the universe into patterns of light and darkness across billions of years. The definition of what counts as a galaxy affects these numbers significantly. At one extreme, you have massive systems like IC 1101, containing trillions of stars spread across enormous volumes of space. At the other end, tiny dwarf galaxies barely qualify for the name, containing just a few million stars held together by dark matter. Some of these dwarf systems are so faint they're difficult to distinguish from large star clusters. Whether you include them in galaxy counts can change the total substantially. As our instruments improve, we keep discovering new dwarf galaxies orbiting our own Milky Way and nearby Andromeda, ghostly companions that remind us how incomplete even our local knowledge remains. Computer simulations provide another way to check our galaxy counts. Projects like Millennium and Illustris start with the known conditions after the Big Bang and watch virtual universes evolve over cosmic time. These simulated universes produce approximately the same number of galaxies we observe in reality, which confirms our understanding of physics, gravity, and cosmic expansion. This cosmic bookkeeping, comparing real observations with theoretical predictions, helps validate our models of how the universe works. When simulated galaxies match observed ones, it suggests we're on the right track with our fundamental physics. The question of galaxy numbers also shifts our perspective on our own cosmic neighborhood. The Milky Way, despite its beauty and complexity, represents just one typical example among 2 trillion similar systems. Each galaxy is unique in its details, but all are built from the same basic ingredients, following the same physical laws. If you could somehow visit these countless galaxies, you'd see familiar patterns repeated everywhere. Spiral arms, glowing cores, star clusters, and gas clouds appear again and again like variations on fundamental themes. This repetition doesn't make the universe boring, it reveals an underlying unity in how cosmic structures form and evolve. Galaxy counts also help measure the universe's expansion rate. By comparing how galaxies are distributed at different distances, astronomers can trace how space has stretched over time. The famous Hubble constant, which describes this expansion rate, was first estimated through observations of galaxy red shifts and brightness measurements. Each galaxy serves as a marker on the ruler of cosmic history, helping us understand not just where we are, but when we are in the universe's ongoing story. As measurements become more precise, they refine our understanding of how the universe has grown and changed. Yet precision, in measurement, always comes with reminders of what remains unknown. Beyond the reach of our most powerful telescopes, light fades into darkness, and we can only speculate about what exists farther out. Perhaps there are galaxy clusters more immense than any we've detected, or individual galaxies larger than we can currently imagine. The observable universe, vast as it appears, might represent just a tiny bubble within something far greater. Our galaxy counts tell us about what we can know, but they also hint at the vastness of what remains beyond our cosmic horizon. In many ways, counting galaxies resembles counting waves on an ocean you'll never finish crossing. Each measurement gives you insight into the rhythm and scale, but the horizon always reveals more complexity. The universe resists being completely catalogued, not because it's hiding information, but because it's genuinely larger than any finite survey can encompass. Every new telescope and deeper observation adds detail, while also revealing new complexities. The numbers may continue changing as our instruments improve, but the sense of awe at the universe's scale remains constant. Among those 2 trillion galaxies, some are far larger, brighter, and more massive than anything we can easily imagine from our small corner of space. Stars exist in patterns that stretch across unimaginable distances. These patterns tell stories written in light and gravity across billions of years. Every galaxy carries the memory of its past, encoded in the way its stars are arranged. The universe doesn't scatter its matter randomly. There's an underlying order, a tendency towards certain shapes that repeat themselves throughout space. It's almost as if the cosmos has preferences, certain ways it likes to organize itself when given enough time and space to work. When people first turned telescopes toward the night sky centuries ago, they saw fuzzy patches of light. They called them nebulae, thinking they were clouds of gas within our own cosmic neighborhood. They noticed these patches came in different forms. Some looked round and smooth, others had delicate spiral patterns. Still others seemed chaotic and torn. It took until the early 20th century for astronomers to realize what they were really looking at. Those fuzzy patches weren't nearby clouds at all. They were entire galaxies, each containing billions of stars, scattered across distances that made the space between planets seem tiny. This discovery changed everything. Suddenly, the universe became much larger, much more complex, and with that complexity came the need to understand why these distant islands of stars took the shapes they did. The classification system that emerged divides galaxies into 3 basic types: spirals, ellipticals, and irregulars. It sounds simple, but within these categories lies the entire story of how matter behaves on the largest scales imaginable. Spiral galaxies are perhaps what most people picture when they think of galaxies. They're the classic shape, the cosmic whirlpool. Our own Milky Way belongs to this family. These galaxies exist as vast, flattened disks, rotating slowly through space. The spiral arms that give them their name aren't solid structures. They're more like waves, regions where stars and gas bunch together as they orbit the galactic center. The arms appear bright because they're where new stars are born. When gas flows into these density waves, it gets compressed, and compression triggers star formation. Young, hot stars burn blue and bright, lighting up the spiral pattern like cosmic neon signs. Between the arms, older, redder stars shine more quietly, creating the contrast that makes the spiral structure visible. Many spirals, including our own galaxy, have bars running through their centers. These aren't the kind of bars you'd find in a tavern, but elongated structures of stars and gas. The bar acts like a cosmic engine, funneling material toward the galaxy's heart, feeding the supermassive black hole that lurks there. From above, a spiral galaxy would look like a giant pinwheel of light. Dense and bright at the center, gradually thinning toward the edges. The whole structure spins, but not like a solid wheel. Stars closer to the center orbit faster than those at the rim, yet somehow the spiral pattern persists for billions of years. This persistence is one of the universe's quiet miracles. How does something so dynamic maintain its shape for so long? The answer lies in the delicate balance between gravity and motion, between the tendency of matter to clump together and the centrifugal forces trying to tear it apart. Spiral galaxies are active places. They're rich in gas and dust, the raw ingredients needed to make new stars. This makes them young at heart. Even if they're billions of years old, they're constantly renewing themselves, turning gas into stars, which eventually die and return material to space, where it can form stars again. But not all galaxies follow this pattern. Elliptical galaxies represent a completely different approach to cosmic organization. Where spirals are flat and structured, ellipticals are puffy and smooth. They look like cosmic footballs or eggs, glowing with the light of trillions of old stars. These galaxies have a different relationship with time. Their stars orbit randomly, not in the organized rotation of a spiral. They've used up most of their gas, so new star formation is rare. The stars they contain are older, redder, gradually cooling as the galaxy ages. The largest galaxies in the universe are ellipticals. They sit at the centers of galaxy clusters, like cosmic monarchs, dominating their neighborhoods through sheer gravitational influence. Some contain more than 1 trillion stars, making our own Milky Way seem modest by comparison. Ellipticals are thought to form through violence. When spiral galaxies collide and merge, their organized structures get disrupted. The collision strips away gas, halts star formation, and scrambles the orderly orbits of stars. What emerges from this cosmic chaos is an elliptical galaxy, a smooth collection of aging stars. In a sense, ellipticals are the graveyards of spirals. They're what happens when galactic evolution reaches a certain endpoint. Their red color and lack of new star formation has earned them the nickname red and dead, though they're very much alive in their own quiet way. Then there are the irregulars, galaxies that refuse to fit into neat categories. They have no clear shape, no obvious pattern. They look chaotic, as if someone shook them up and scattered their stars randomly. Many irregulars are small, their shapes distorted by the gravitational pull of larger neighbors. The Magellantic Clouds, visible from the southern hemisphere, are examples. These companion galaxies to the Milky Way have been stretched and warped by our galaxy's gravity. Other irregulars are young, still forming from primordial clouds of gas. They haven't had time to settle into the stable disk structure of a spiral. They're cosmic teenagers, awkward and undefined, still figuring out what they want to be when they grow up. Between these main categories exist intermediate types. Lenticular galaxies have the disk shape of spirals, but lack visible arms. They're like spirals that have lost their gas. Unable to form new stars but still maintaining their basic structure. They represent a middle stage in galactic evolution, caught between youth and old age. Each galactic shape reflects the environment where it formed. Spirals tend to exist in quieter regions of space, where collisions are rare and gas remains available for star formation. Ellipticals are more common in dense galaxy clusters, where interactions are frequent and violent. This relationship between environment and form reveals something profound about the nature of cosmic evolution. Galaxies aren't isolated objects. They're shaped by their surroundings, by the invisible web of dark matter that connects them, by the dance of gravity played out over cosmic time. The shapes we see today aren't permanent. Galaxies can transform from one type to another. A spiral can become an elliptical through merger. An irregular can evolve into a spiral, given enough time and the right conditions. The universe is patient, willing to spend billions of years reshaping its contents. There's something almost artistic about this process. The universe as sculptor, using gravity as its tool, slowly molding matter into forms both beautiful and functional. Each galaxy is a unique creation, yet they all follow the same basic physical laws. When we look at distant galaxies, we're seeing them as they were millions or billions of years ago. Light takes time to travel, so we're witnessing different stages of galactic evolution simultaneously. Some galaxies appear young and irregular. Others show the mature spiral structure of middle age. Still others display the smooth elliptical form of old age. This temporal dimension adds another layer to the story. Galaxies aren't just objects in space, they're objects in time. They're objects in time. Their shapes encode their histories, their future possibilities, their place in the grand narrative of cosmic evolution. The study of galactic shapes reveals the universe's tendency toward both order and chaos. Order in the repeated patterns that emerge from simple physical laws. Chaos in the random interactions and collisions that disrupt those patterns. The tension between these forces creates the diversity we observe. Perhaps there's a lesson here about change and permanence. Galaxies seem eternal from our perspective, but they're actually dynamic, constantly evolving. Their apparent stability is maintained through continuous motion and interaction. It's a reminder that even the most permanent-seeming structures are actually in constant flux. The classification of galaxies also reflects humanity's desire to understand and categorize the natural world. Faced with the overwhelming diversity of cosmic structures, we create simple frameworks to make sense of what we observe. These frameworks are tools for understanding, not rigid boundaries. The universe, as always, is more complex and nuanced than our categories can fully capture. When astronomers look through their telescopes, they see galaxies scattered across space like jewels on black velvet. Each one tells a story written in starlight. The way we classify these cosmic structures, it gives us a common language, a way to make sense of what seems like chaos. But here's something remarkable. Galaxies aren't frozen in time. They're constantly changing, evolving, reshaping themselves over millions and billions of years. That beautiful spiral you might see in a photograph, it could become something completely different, given enough time. What appears permanent is really just a snapshot of an ongoing transformation. The light that reaches us from these distant galaxies, it carries secrets about what's happening inside them. Spiral galaxies glow brightly in ultraviolet and infrared wavelengths. This tells us they're rich in gas and dust, actively forming new stars. Those young, hot stars burn bright and fast, heating up the surrounding material until it shines. Elliptical galaxies paint a different picture entirely. They emit mostly visible and near-infrared light, the signature of older, cooler stars. These are galaxies that have settled into a quiet middle age, their star formation days mostly behind them. Irregular galaxies, well, they're unpredictable. Some regions blaze with new star birth while others remain dim and quiet. By studying these different wavelengths of light, astronomers can piece together a galaxy's biography. They can tell how old it is, how active its stellar nurseries are, what it's made of. Light becomes a messenger, carrying news from across the universe. The shapes of galaxies also affect how they move through space. In spiral galaxies, stars follow relatively orderly paths, circling the center like cars on a cosmic highway. But in elliptical galaxies, stellar motion is more chaotic. Stars zip around in all directions, following elongated orbits that intersect and cross over each other. These movement patterns influence everything about a galaxy's life: how it holds together, how it evolves, how it interacts with its neighbors. Even the invisible dark matter that surrounds each galaxy takes on different shapes. Spiral galaxies have flattened halos that mirror their disc-like structure. Ellipticals are wrapped in more spherical cocoons of dark matter. This dark matter, it's one of the universe's greatest mysteries. We can't see it directly, but we know it's there because of how it affects the things we can observe. Without dark matter, spiral galaxies would tear themselves apart. Their outer stars move so fast they should fly off into empty space, but they don't. Something invisible is holding them in place. When you browse through images of distant galaxies, the variety is breathtaking. Some spirals have arms wound tight, like clock springs. Others spread their arms wide, loose, and graceful. Some ellipticals are perfect spheres, others slightly squashed. Irregular galaxies run the gamut from faint smudges to brilliant star factories. Each shape represents a unique history, a particular set of circumstances that led to that specific arrangement. It's like looking at faces in a crowd, each one distinct, each one shaped by its own story. Our Milky Way sits somewhere in the middle of this cosmic spectrum. It's not too big, not too small, not too active, not too quiet, just balanced enough to provide a stable home for billions of years. If you were designing a galaxy from scratch, trying to create the perfect environment for planets and life, you might come up with something very much like ours. Scientists use these galactic shapes to understand how the entire universe has evolved. In the early days after the Big Bang, most galaxies were small and chaotic. The elegant spirals and smooth ellipticals we see today, they're the result of billions of years of growth and collision and merger. When we observe very distant galaxies, we're literally looking back in time. The light from those galaxies has traveled for so long to reach us that we see them as they were billions of years ago. It's like watching cosmic evolution in slow motion, seeing the messy early universe gradually organize itself into the structured cosmos we inhabit today. Galaxies don't live in isolation. They're social creatures, constantly influenced by their neighbors. In crowded regions of space, galaxies pull on each other with gravity, distorting their shapes, stealing their gas and stars. These interactions can trigger spectacular bursts of star formation or strip a galaxy bare, leaving it dim and lifeless. Spiral galaxies that wander into dense clusters often lose their characteristic shape. The hot gas that fills these cosmic cities steals away the raw material needed for making new stars. These spirals fade into something more subdued, their star-forming days cut short by their environment. Our Milky Way enjoys a relatively quiet neighborhood. We have a few close companions, but plenty of space to breathe. This cosmic tranquility has allowed our galaxy to maintain its spiral structure for billions of years. But change is coming. In the distant future, we'll collide with our nearest large neighbor, Andromeda. When that happens, the result will likely be a single, large elliptical galaxy. Even this future transformation follows patterns observed throughout the universe. Spirals merge, their collision triggers massive waves of star formation, then everything settles down into a smooth, rounded glow. It's a cosmic life cycle, played out over unimaginable spans of time. If you could speed up time and watch galaxies evolve, they would seem almost alive. Spirals would pulse and breathe, their arms tightening and loosening. Ellipticals would grow larger as they absorbed smaller galaxies. Irregulars would dance and twist before dissolving into new configurations. The shapes we catalogue today, they're just temporary expressions of ongoing processes. The universe never stops rearranging itself, never stops finding new ways to organize matter and energy. There's something profound in this endless variety of galactic forms. It represents a delicate balance between order and chaos. Gravity works to create structure, to pull matter into organized patterns. But interactions and collisions gradually break down that order, leading to simpler, more uniform arrangements. We live in a special time, cosmically speaking. Enough time has passed since the Big Bang for complex structures to emerge, but not enough time for everything to fade into bland uniformity. The universe is showing off its creativity while it still can. When we talk about the shape of starlight, we're really describing how gravity sculpts luminous matter over cosmic time. Every spiral arm, every elliptical halo, every irregular patch of brightness, it all comes from the same simple principle. Mass attracts mass. From this one rule springs forth the entire menagerie of galactic forms we observe. Despite their vastly different appearances, all galaxies share certain fundamental qualities. They all harbour stars that are born, live their lives, and die. They all recycle the chemical elements forged in stellar cores. They all obey the same physical laws. Their shapes may vary wildly, but their essence remains constant. Collections of starlight, bound together by gravity, evolving through deep time. If you could somehow travel from galaxy to galaxy, drifting through the cosmic web, you'd witness this diversity firsthand. A brilliant spiral might give way to a ghostly elliptical, then to a small, irregular galaxy, hanging alone in the darkness. Each would have its own character, its own rhythm of stellar birth and death, its own quiet story written in the language of light. Together, they form the grand tapestry of our universe, an endless variety built from the same basic ingredients, shaped by the same invisible forces. Somewhere in this vast collection, one particular spiral galaxy turns slowly through space. From the outside, it's unremarkable, just another patch of light, among billions. But from the inside, from our perspective, it contains everything we've ever known, or ever will know. Our entire existence plays out within the gentle embrace of its spiral arms. When we consider where our cosmic home sits in the vast landscape of galaxies, we find ourselves confronting a curious truth about scale and perspective. The Milky Way, which feels boundless from our tiny vantage point, turns out to be remarkably ordinary when measured against the full spectrum of galactic giants and dwarfs that populate the universe. Picture this: the galaxy we call home stretches roughly 100,000 light-years from edge to edge. Even traveling at light speed, 300,000 kilometers every single second, you'd need a full century of millennia just to cross from one side to the other. That's the kind of distance that makes our everyday measurements feel almost laughably small. Yet in the cosmic census, this vast expanse places us squarely in the middle, neither among the true giants nor the cosmic runts. The structure itself tells a fascinating story about balance and motion. Our galaxy is extraordinarily flat, like a cosmic pancake spinning slowly through the darkness. The entire disk measures only about 1,000 light-years thick, compared to its 100,000 light-year width. Within this slim rotating sheet, somewhere between 100 and 400 billion stars make their endless orbits. The range is so wide because counting stars across such distances, through clouds of dust and gas, remains impossibly difficult. What strikes many astronomers as particularly intriguing is that planets likely outnumber stars in our galaxy. Current estimates suggest several 100 billion worlds scattered throughout those spiral arms, most of which we'll never see, never catalogue, never know. Even if only the tiniest fraction resembles Earth in any meaningful way, we're still talking about billions of potentially habitable worlds, each one a possible stage for stories we can barely imagine. The invisible architecture holding everything together presents one of modern astronomy's most compelling mysteries. Dark matter, that unseen scaffold of the universe, makes up roughly 90% of our galaxy's total mass. The Milky Way weighs in at something like 1 to 1.5 trillion times the mass of our Sun, but only a small fraction of that consists of stars, gas, and dust, the stuff we can actually observe. The rest exists as this ghostly presence, detectable only through its gravitational influence. This hidden framework extends far beyond what we can see, forming a spherical halo that may reach 200,000 light-years in radius. Without it, the stars in the outer regions would simply fly apart, their orbital speeds too high for the visible matter alone to hold them in place. Dark matter fills that gap, providing the gravitational glue that keeps our cosmic neighborhood intact. When astronomers compare the Milky Way to its neighbors, our galaxy's middling status becomes even more apparent. Andromeda, our nearest major companion, spans about 220,000 light-years and carries roughly twice our mass. Many other spirals cluster around similar dimensions. The smallest spiral galaxies measure only tens of thousands of light-years across, while the largest approach 200,000 or 300,000, beyond that scale entirely. The true monsters of the universe, those massive elliptical galaxies lurking at the centers of galaxy clusters, can reach over 1 million light-years in diameter. This cosmic modesty actually works in our favor, though. Giant galaxies typically form through violent collisions that can disrupt their internal structure, heat their gas to temperatures that shut down star formation, and generally create chaos that lasts for billions of years. The Milky Way has managed to avoid that kind of catastrophic merger for most of its existence. Sure, it's absorbed smaller dwarf galaxies over time, leaving faint stellar streams as evidence of these ancient meals, but no major collision has disrupted its basic architecture since its earliest days. That relative peace has allowed our galaxy to maintain what astronomers call a steady star formation rate. Each year, the Milky Way converts gas and dust into new stars equivalent to about 1 or 2 solar masses. Across billions of years, this seemingly modest rate adds up to entire generations of starlight, each one enriching the galaxy's chemical composition through the eternal cycle of stellar birth and death. The process unfolds primarily along the spiral arms, where density waves compress gas into the conditions needed for gravitational collapse. These stellar nurseries remain hidden by dust until the newborn star's radiation clears away their surrounding cocoons. In infrared light, these regions glow with the heat of star formation, tracing the slow, steady rhythm that has continued for billions of years. Meanwhile, older stars complete their life cycles, returning processed material to the interstellar medium. Supernovae scatter heavy elements throughout space, enriching the raw materials for future stellar generations. Our Sun, formed about 4.5 billion years ago, represents the product of this long chemical evolution. The iron in our blood, the calcium in our bones, the oxygen we breathe, all originated in the nuclear furnaces of previous stellar generations within this very galaxy. The Milky Way's environment also reflects its moderate nature. Rather than residing in a dense galaxy cluster, we inhabit a small group containing about 30 known members, most of them dwarf galaxies. Our two largest companions, the Large and Small Magellanic Clouds, orbit nearby as gravitationally bound satellites. These smaller galaxies are slowly being stripped of their gas by tidal forces, creating streams that stretch across hundreds of thousands of light years. This ongoing process represents how galaxies like ours typically grow, not through constant major mergers, but through the gradual accretion of smaller companions. Eventually, the Magellanic Clouds will likely merge with us entirely, adding their stars to our collection in a process so gradual that it unfolds over billions of years. The galaxy's shape bears the subtle signatures of this dynamic evolution. The disk isn't perfectly flat, but shows a gentle warp, with one side bending slightly upward and the other downward. These distortions likely result from gravitational interactions with the Magellanic Clouds, or the dark matter halo itself, reminding us that even in apparent calm, our galaxy continues to flex and adjust like a living thing. Our spiral structure adds another layer of complexity to this cosmic architecture. The Milky Way displays four major arms: Perseus, Scutum Centaurus, Norma, and Sagittarius Carina, connected by smaller spurs and bridges. The Sun occupies one of these minor features, the Orion Arm, positioned roughly halfway between the galactic center and edge. From this relatively quiet location, our entire solar system orbits the galaxy every 230 million years, traveling at about 800 kilometers per hour. Despite this tremendous motion, the stars appear fixed in our sky because the distances involved are so immense. Everything moves together in a stately cosmic dance, so slow and vast that it appears frozen from our limited perspective. Yet this motion carries us through different regions of the galaxy over geological time, potentially exposing Earth to varying levels of cosmic radiation and gravitational influences. Looking toward the galactic center, in the constellation Sagittarius, we're peering toward one of the most extreme environments in our cosmic neighborhood. There, a supermassive black hole called Sagittarius A star, weighing about 4 million times the mass of our Sun, anchors the entire galaxy through its gravitational influence. Dense star clusters and swirling gas clouds surround this invisible monster, revealed through radio and infrared observations that can penetrate the dust blocking our optical view. Despite its enormous mass, this central black hole remains relatively quiet compared to the active galactic nuclei found in many other galaxies. Only a small trickle of material currently falls into it, allowing our galaxy to maintain its peaceful demeanor. For now, it rests, and our entire cosmic home rests with it. The outer reaches of the Milky Way tell stories of ancient history through globular clusters, those spherical collections of hundreds of thousands of stars bound tightly together. These stellar fossils orbit far above and below the disk, many containing stars more than 10 billion years old, nearly as ancient as the universe itself. They represent remnants of the smaller systems that merged together during our galaxy's formation, preserved like archaeological artifacts from cosmic prehistory. In terms of brightness, the Milky Way radiates with the light of roughly 10 billion suns. While this might seem overwhelming by human standards, the largest galaxies can outshine us by factors of 10 or more. Our luminosity marks us as typical of mature spiral galaxies, neither faint nor dazzling, but balanced between extremes. The overall color appears as soft white with a slight yellow tint, reflecting the mixture of young blue stars and older red ones scattered throughout the disk. From a distant vantage point, our entire galaxy would appear as a glowing disk of pale light against the cosmic dark unremarkable among the billions of other galaxies, scattered throughout observable space. This ordinariness, this cosmic mediocrity, might seem disappointing at first glance. We're not the biggest, not the brightest, not the most unusual galaxy in the universe. Yet perhaps there's something profound in this averagence, this position right in the middle of galactic possibility. The Milky Way represents a kind of cosmic archetype, the galaxy you might imagine when picturing a spiral. It's balanced between youth and age, activity and calm, chaos and order. This stability has allowed complex chemistry to develop over billions of years, planets to form and evolve, and ultimately, life to emerge and contemplate its place in the vast cosmic web. Our galaxy's modesty may actually be its greatest strength, providing the kind of stable, long-term environment where remarkable things can unfold slowly, quietly, over the immense spans of time that cosmic evolution requires. Our galaxy sits at a fascinating moment in time, roughly 13 billion years after the first galaxies began to take shape. When we think about cosmic history, we're living right in the middle of it all. The universe has been around long enough for complex structures to develop, but it's still young enough to keep making new stars. There's something almost poetic about existing during this cosmic sweet spot. The Milky Way embodies this perfect timing. It's old enough to have found its stability, yet young enough to stay active and vibrant, in a cosmos filled with extremes. From massive elliptical galaxies burning bright in distant clusters, to tiny dwarf galaxies barely flickering in the void, our home galaxy occupies a comfortable middle ground. This cosmic moderation might actually be the secret to its success. When scientists study galaxies across the universe, they often discover that our Milky Way falls right into the median range for almost everything. Its total mass, even its brightness, all cluster around the statistical middle. It's like the universe's most average galaxy, and that averagence might be exactly what makes it special for creatures like us. Our neighboring galaxy Andromeda stretches slightly larger and carries more mass than we do. The Triangulum galaxy, another member of our local cosmic neighborhood, runs smaller than both of us. These three galaxies create a miniature hierarchy in our corner of space that step back further, and the perspective shifts dramatically. About 50 million light-years away, the Virgo cluster contains galaxies of every imaginable type and size. Some of those cosmic giants dwarf all three galaxies in our local group combined. That's where the true monsters of the galaxy world live, in those crowded cosmic cities where galaxies jostle for space. But there's profound wisdom in our galaxy's modest proportions. Size isn't everything in the cosmic real estate market. The Milky Way hit a sweet spot that's almost too perfect to be accidental. It's large enough to keep forming stars for billions upon billions of years, yet small enough to maintain its structural stability. It's isolated enough to avoid constant cosmic collisions, but rich enough in heavy elements to build the complex chemistry that planets and life require. If we ranked galaxies by their ability to host life rather than their raw size or brightness, our Milky Way would score near the top of the list. It's like the universe's most livable neighborhood, not flashy or overwhelming, just perfectly balanced for the long game of cosmic evolution. Picture scaling galaxies down to sizes we can wrap our minds around. Those massive elliptical galaxies would become sprawling metropolitan areas, blazing with light and cosmic activity around the clock. Our Milky Way would be more like a well-planned mid-sized city, not small or provincial, but genuinely livable and thoughtfully organized. It would have quiet, residential neighborhoods of stars, long tree-lined avenues of stellar systems, each solar system like its own house, with its own unique story to tell. From this perspective, the Milky Way's moderation becomes almost elegant, big enough to contain genuine wonders, yet small enough to feel somehow familiar and comprehensible. Even when we call it modest, the scale remains absolutely staggering by human standards. Light that started its journey from the far edge of our galactic disk, when early humans first learned to control fire, is only reaching us right now. The photons hitting your eyes tonight began their trek across space when our ancestors were just figuring out the basics of civilization. Our nearest major galactic neighbor, Andromeda, appears relatively close in those beautiful space photographs, but it sits a mind-bending 2.5 million light-years away. Even the faintest dwarf galaxies that orbit around us maintain distances of hundreds of thousands of light-years. All of this vast emptiness and distance exists within the framework of what we casually call our local galactic neighborhood. When you see the number written out, 100,000 light-years across, it looks manageable on paper, just a few digits in a row. But when you try to imagine that distance as actual space you'd have to cross, It becomes something beyond human comprehension. And yet, among the billions of other galaxies scattered throughout the observable universe, this incomprehensible scale represents perfectly average, completely typical galactic real estate. The universe contains countless spiral galaxies similar to ours, some running smaller, others stretching larger, all rotating slowly through the same dark cosmic ocean. We simply happen to inhabit this particular one, the specific galaxy whose stars forged the heavy elements that eventually became the atoms in our bodies. It's the galaxy whose careful balance of size and serenity created just the right conditions for life to emerge on a small blue world orbiting near one of its middle spiral arms. Our cosmic home is modest by universal standards. Absolutely. But it turns out to be perfectly calibrated to host beings capable of pondering what modesty even means when measured against the infinite. Imagine trying to understand what it means to belong somewhere. In the cosmos, even galaxies need companionship. They don't drift through space as lonely wanderers, but instead gather into families, held together by invisible threads of gravity. Our Milky Way galaxy lives in one of these cosmic neighborhoods, called the local group. It's a relatively small gathering, as galaxy clusters go, but it contains everything we can ever directly observe from our home. The entire structure spans roughly 10 million light-years across, which creates a fascinating boundary in space. Within this boundary, gravity wins the eternal tug-of-war against the expansion of the universe. Outside of it, space itself stretches so rapidly that galaxies drift apart forever, never to meet again. Inside, the galaxies dance together in an ancient choreography, orbiting their shared center of mass on timescales that dwarf the entire history of stars. This dance moves so slowly that it appears almost frozen to us. The rhythms of galactic motion unfold over billions of years, making our human perception of time seem like a brief flicker. Yet this apparent stillness conceals constant motion, constant change, constant interaction. Two massive spiral galaxies dominate this cosmic family. Our Milky Way sits near one edge of the group, while the Andromeda Galaxy, also known as M31, occupies the opposite side. Between them stretches a gulf of 2.5 million light-years, vast by any human measure, yet surprisingly intimate in cosmic terms. These two giants are slowly approaching each other, drawn together by their mutual gravitational attraction. They move toward each other at about 110 kilometers per second, fast enough to circle Earth in just over 6 minutes, yet glacially slow by astronomical standards. In approximately 4 billion years, they will merge, creating a single, larger galaxy. This future collision raises profound questions about permanence and change. Everything we see around us, every star in our night sky, will eventually become part of a different galaxy entirely. The constellations our ancestors used for navigation will be scrambled and reformed in ways we cannot imagine. Between these two galactic titans lies a third notable spiral, the Triangulum Galaxy, designated M33. It measures about 60,000 light-years across roughly half the diameter of the Milky Way. This galaxy may orbit Andromeda as a smaller companion, creating a hierarchy within our cosmic neighborhood. Triangulum glows with active star formation, its spiral arms lit up by clusters of young blue stars and pink nebulae of ionized hydrogen gas. These star-forming regions represent galactic youth, areas where new suns are still being born from clouds of cosmic dust and gas. Around these three major galaxies orbit dozens of smaller companions, most of them dwarf galaxies containing only millions of stars, compared to the hundreds of billions found in larger spirals. The Milky Way alone hosts more than 50 known satellite galaxies, with new ones still being discovered as our telescopes become more sensitive. Some of these dwarf companions shine brightly enough to see with simple instruments. The large and small Magellanic Clouds appear as faint, misty patches in southern skies, visible to the naked eye as smudges of light near the edge of the Milky Way. Other satellite galaxies remain so dim that they were only discovered in recent decades, their feeble light barely distinguishable from the background glow of space. The large Magellanic Cloud spans about 14,000 light-years across, making it the largest of our galactic companions. It's classified as an irregular galaxy, its shape distorted by the gravitational pull of our own Milky Way and by its smaller partner, the Small Magellanic Cloud. These two clouds orbit our galaxy together, trailing behind them long streams of hydrogen gas, known as the Magellanic Stream. This stream stretches across hundreds of thousands of light years, wrapping around the Milky Way like a faint ribbon of material pulled away by tidal forces. Eventually, this stolen gas will fall into our galaxy, where it will fuel new generations of star formation. This represents a kind of cosmic recycling, a quiet process of galactic cannibalism that has been occurring for billions of years. Larger galaxies grow by consuming their smaller neighbors, incorporating their material into new stars and planetary systems. Beyond the bright Magellanic Clouds lie numerous other dwarf companions, with names like Sculptor, Fornax, Draco, and Ursa Minor. These faint galaxies orbit far from the Milky Way's main disk, like scattered embers circling a campfire, following long, slow paths through space. Most of these dwarf galaxies contain more dark matter than visible matter. The stars we can see represent just a tiny fraction of their total mass. The rest consists of mysterious dark matter, detectable only through its gravitational effects. These galaxies are fragile structures, easily disrupted by the tidal forces of their larger companions. Some dwarf galaxies are already being torn apart by our galaxy's gravity. The Sagittarius dwarf galaxy is currently in the process of merging with the Milky Way, its stars scattered into long streams that arc across our galactic halo. We are witnessing the slow death of an entire galaxy, played out over hundreds of millions of years. Andromeda Galaxy hosts its own collection of satellite companions, more than 30 known systems orbiting around it. Among the most prominent are two dwarf elliptical galaxies, M32 and M14, which lie close enough to Andromeda to appear in the same telescope field of view. M32 appears compact and dense, possibly the stripped core of a larger galaxy that was consumed long ago in some ancient galactic collision. M110 spreads out more diffusely, a faint oval collection of older reddish stars. Both represent different outcomes in the complex ecology of galaxy interactions. The space between galaxies in the local group is not empty, though it approaches the best vacuum we can create on Earth. A few atoms per cubic meter drift through this intergalactic medium, along with invisible filaments of dark matter that bind the entire group together into a single gravitational system. These dark matter filaments connect all the galaxies like an invisible web, determining their motions and interactions over cosmic time. The structure they create resembles a vast scaffolding upon which ordinary matter hangs, forming the stars and planets we can actually observe. The entire local group moves as a single unit through space, heading slowly toward the Virgo cluster, the nearest large collection of galaxies located about 50 million light-years away. This motion suggests that even our cosmic neighborhood belongs to something larger, part of an even grander structure in the universe's architecture. This raises questions about scale and belonging that stretch the limits of human comprehension. We live on a planet orbiting a star, which orbits in a galaxy, which moves in a group of galaxies, which flows toward a cluster of galaxy groups. Each level of organization seems to require the next, creating hierarchies of cosmic structure that extend far beyond what we can directly perceive. The local group exists as this cosmic neighborhood, where every single galaxy moves in a complex three-dimensional ballet. When we map it out on paper, it might look like random scattered dots, but the reality involves this intricate gravitational choreography that's been unfolding for billions of years. The Milky Way and Andromeda serve as the two primary performers in this dance. They're moving toward each other, destined for a collision that will happen roughly 4.5 billion years from now. All the smaller galaxies, the dwarf systems, orbit around these two giants, following paths that will eventually lead them into whatever larger structure emerges from that merger. Here's something fascinating about cosmic time. If we could somehow speed up this entire process by 1 billion times, we'd watch these galaxies weaving through space like dancers on a stage. The dwarf galaxies would approach the larger ones, get stretched by tidal forces, then gradually dissolve into them. The spiral arms of the big galaxies would twist and bend as they influence each other across the void. When Andromeda and the Milky Way finally do collide, their gravitational halos will overlap long before their visible disks actually touch. The collision itself will unfold over hundreds of millions of years. Tidal forces will pull long streams of stars out of both galaxies, creating these beautiful arcs that bridge the space between them. Gas clouds will smash together, triggering massive bursts of star formation across both systems. The supermassive black holes at the center of each galaxy will spiral toward each other, eventually merging in an event that releases tremendous amounts of energy. The final result will be a single, large elliptical galaxy, sometimes called Milky Way or Milky by astronomers. Those distinctive spiral arms we see today will vanish completely, replaced by a smooth, featureless glow. Our Sun, if it still exists at that point, will find itself in a completely different orbital pattern within this new galaxy. The ordered motion we see today will become randomized by the merger process. Yet, this kind of galactic collision represents something completely normal in cosmic evolution. It's actually how galaxies grow over time. The local group we observe today is really just a snapshot of one stage in this ongoing process. In the distant past, there were probably many more small member galaxies, most of which have already been absorbed by the larger ones. In the future, fewer independent galaxies will remain as the surviving dwarfs get pulled into the bigger systems. Gravity operates with infinite patience. It never stops working, never takes a break. The local group is slowly but inevitably evolving toward unity, toward becoming a single gravitational system. Even right now, we can see faint evidence of past mergers in the outer regions of both the Milky Way and Andromeda. Streams of stars too dim to see with our eyes alone arc across the sky. These represent the remnants of dwarf galaxies that were consumed long ago. The Gaia spacecraft has mapped some of these stellar streams in remarkable detail, showing us that much of our galaxy's outer halo was actually built from smaller galaxies that fell in over cosmic time. These ancient stars still carry distinct chemical signatures, like fingerprints that reveal their origins. It's a reminder that galaxies, much like living things, carry traces of everything they've encountered throughout their history. Every interaction leaves a mark, a record written in the motion and composition of stars. The local group's relatively small size makes it an ideal laboratory for studying galactic evolution. Astronomers have mapped, measured, and modeled every single member. We know the distances between them, we track their motions, we understand their relationships. The physics at work here, gravity and dark matter and gas dynamics, operates the same way in much larger galaxy clusters, just at different scales. Imagine standing at the very edge of the Milky Way's halo and looking outward. Andromeda would dominate your view, appearing as a disk of light, stretching several times wider than our full moon, though far too faint to see without some kind of magnification. You'd be able to make out its spiral structure as delicate swirls, and its bright central region would glow with the combined light of hundreds of billions of stars. Its satellite galaxies would cluster around it like tiny fireflies. The space between our galaxy and Andromeda would appear completely empty, yet gravity would be working invisibly, drawing the two systems together at an imperceptible rate. Further out, the Triangulum galaxy would shine as a smaller, dimmer point of light. And beyond that, the dwarf members of the local group would appear as faint smudges scattered across the cosmic darkness. Looking even further out, you might glimpse the faint outline of the Virgo cluster, its thousands of galaxies blending into a soft, hazy glow. The local group is actually drifting toward that massive cluster, but it will never become part of it. The expansion of the universe itself will carry our little group away, faster than gravity can pull it in toward Virgo. Eventually, many billions of years from now, the local group will become this isolated island in an expanding cosmos, surrounded by empty darkness, its remaining galaxies merged into a single system. There's something both melancholy and beautiful about that cosmic destiny, the idea that our galactic neighborhood will eventually find itself alone in an ever-expanding universe. For now, though, the local group remains this interconnected family. Each galaxy exerts gravitational influence on all the others, but the motions unfold slowly and steadily. It's a system in a kind of equilibrium, a cosmic neighborhood, where dramatic events happen on timescales almost too vast to comprehend, yet where nothing ever truly stops moving. The Milky Way satellite galaxies circle quietly in their orbits. Andromeda's companion systems trace their own complex paths. Triangulum drifts nearby, and astronomers still debate whether it's actually orbiting the larger galaxies or just passing through the neighborhood. It's a kind of galactic choreography that requires enormous patience to observe and understand. There's something deeply comforting in knowing that our galaxy doesn't travel through space alone, that it moves in the company of other star systems. The distances involved are staggering, millions of light years separating the major members, but the gravitational bonds connecting them are absolutely real and measurable. Even in what appears to be empty space between galaxies, invisible connections persist. The gravitational influence of one system shapes the structure and motion of others. The collective light of hundreds of billions of stars in one galaxy affects the evolution of its neighbors. The entire group moves together through the cosmic dark, this small gathering of light, in an essentially infinite sea. Somewhere within one of those spirals, on a relatively small planet, orbiting a fairly ordinary star, we've developed the capacity to look outward and recognize all of this structure and motion. We can measure these vast distances, imagine these cosmic timescales, and begin to understand our place in this gravitational dance. We're participants in this cosmic ballet, even though our individual steps are far too small to detect or influence the larger choreography. The night sky holds secrets that stretch back billions of years, and among all the cosmic neighbors surrounding our Milky Way, one galaxy commands special attention. Andromeda stands as our closest large companion, not some distant faint smudge, but a genuine rival in size and complexity. This massive spiral galaxy, catalogued as M31, by astronomers represents both our nearest galactic neighbor and our ultimate destiny. Light takes an extraordinary journey to reach us from Andromeda. Every photon that touches our eyes tonight began its travels 2.5 million years ago, when that ancient light first departed from Andromeda's trillion stars. Early humans hadn't yet appeared on Earth. The photons have been racing through empty space, carrying the image of a distant galaxy, while entire species evolved and vanished on our planet below. On clear nights, away from city lights, you can actually spot Andromeda without any equipment. It appears as a pale, elongated blur, barely visible to the naked eye. That fuzzy patch contains more stars than the human mind can truly comprehend. 1 trillion individual suns, each potentially hosting planets, each burning with nuclear fire. The scale of Andromeda humbles our own galaxy. Its spiral disk stretches about 220,000 light-years across, making it more than twice as wide as the Milky Way. The total mass, including all the mysterious dark matter surrounding it, reaches somewhere between 1.5 to 2 trillion times the mass of our Sun. Most studies suggest Andromeda outweighs the Milky Way, though the exact measurements remain uncertain. Through telescopes, Andromeda reveals its tilted orientation, allowing astronomers to study its structure in remarkable detail. Sweeping spiral arms curve outward from a brilliant central bulge traced by dark lanes of interstellar dust. These dust lanes mark where gas and debris concentrate, the raw materials for future star formation. At the very center, billions of ancient stars crowd around a supermassive black hole, creating an intensely bright core. Faint streams of stars arc beyond Andromeda's main disk, like scattered breadcrumbs telling stories of cosmic cannibalism. These stellar streams are the digested remains of smaller galaxies, absorbed over billions of years. Andromeda has grown through galactic consumption, methodically incorporating its smaller neighbors into its expanding structure. Both the Milky Way and Andromeda share fundamental similarities. They're both barred spiral galaxies. Both contain supermassive black holes at their hearts, and both continue forming new stars. Yet, Andromeda seems to possess a different personality, if galaxies can be said to have personalities. It shines more brightly, rotates slightly faster, and creates stars at a higher rate than our home galaxy. Perhaps most intriguingly, Andromeda's center contains not one, but two distinct clusters of stars, orbiting around their shared gravitational center. This double nucleus likely resulted from a major galactic merger in the distant past, when Andromeda consumed another large galaxy. The collision scattered stars into new arrangements, creating this unusual dual structure. In many ways, Andromeda feels like an older, more mature version of the Milky Way. Its halo extends further, contains more debris from past mergers, and shows the scars of a more violent evolutionary history. Looking at Andromeda might be like glimpsing our own galaxy's future, a preview of what the Milky Way could become given enough time and cosmic encounters. The space separating these two galaxies isn't truly empty. Tenuous gas fills the void, along with invisible threads of dark matter connecting their extended halos. In fact, the outer reaches of both galaxies already overlap, though their visible spiral disks remain far apart. The gravitational attraction between them grows stronger over time, slowly overcoming the expansion of space itself. This mutual attraction creates an inevitable cosmic appointment. Andromeda and the Milky Way are approaching each other at roughly 110 kilometers per second. That might sound fast, but across such vast distances, their meeting will take billions of years to unfold. Astronomers have calculated this future collision with surprising precision, using data from space telescopes to track Andromeda's motion through space. The first close encounter will occur in approximately 4 billion years. When that time arrives, both galaxies will pass through each other like ghostly ships in the night. Individual stars rarely collide directly because the spaces between stars are so immense. Instead, gravitational tides will stretch and distort both spiral disks, pulling out long tails of stars and gas into space. After their first passage, both galaxies will swing apart, then gradually fall back together for another encounter. This cosmic dance will repeat several times over the following billion years, each approach bringing them closer together until they finally settle into a single, merged system. The collision will transform both galaxies completely. Their orderly spiral structure will dissolve into the random motions of an elliptical galaxy. The organized rotation that creates spiral arms will give way to chaotic stellar orbits. Gas clouds will collide and compress, triggering intense bursts of star formation before the remaining fuel gets consumed or expelled entirely. Deep at the centers of both galaxies, the supermassive black holes will begin their own merger process. As they spiral closer together, they'll emit gravitational waves, ripples in space-time itself. When these black holes finally unite, the energy released will briefly shake the fabric of the universe, before settling into a single, even more massive black hole. The combined galaxy, sometimes playfully called Nilkomeda or Nilka, will shine as a giant elliptical system. It will contain all the stars from both predecessors, but arranged in a completely different structure. The familiar spiral arms will be gone forever, erased by the gravitational chaos of the collision. If intelligent life still exists during this merger, the night sky will offer spectacular views. Long before the final combination, Andromeda will grow larger and brighter in Earth's sky, transforming from a faint smudge into a glowing disk visible to the naked eye. Its spiral structure will become clearly visible without telescopes, stretching across a significant portion of the sky. As the galaxies approach each other, bridges of stars will form between them, creating luminous arcs connecting the two systems. The familiar band of the Milky Way will distort and twist, its symmetry broken by Andromeda's gravitational influence. For hundreds of millions of years, observers will witness double spirals dancing across the heavens, two galaxies locked in their final embrace. Despite the dramatic scale of this galactic collision, it won't be destructive in any violent sense. The vast distances between individual stars make direct impacts virtually impossible. Most stars will simply find themselves following new orbital paths in the merged system. What changes dramatically is the overall structure, the gas distribution, and the patterns of star formation. When interstellar gas clouds collide, they compress and heat up, igniting waves of new star formation. The night sky will blaze with clusters of young blue stars, the brilliant offspring of these cosmic encounters. The merger represents transformation rather than destruction, a fundamental reorganization of matter and energy. The relationship binding the Milky Way and Andromeda demonstrates cosmic inevitability in its purest form. Gravity ensures their eventual meeting, while time provides the mechanism for their approach. Currently, they exist as two magnificent spirals, their light crossing the emptiness between them, their mutual attraction growing stronger each passing year. Evidence suggests these galaxies may have encountered each other before, perhaps 10 billion years ago, when the universe was much younger. If true, then Andromeda and the Milky Way have been gravitationally linked for most of cosmic history, engaged in an extraordinarily slow orbital dance that will end only when they become permanently united. One of Andromeda's most remarkable features is its enormous halo, extending over 1 million light-years from the galaxy's center. This halo contains roughly as much mass as the visible galaxy itself, filled with hot gas and ancient stars scattered by past galactic encounters. If this halo were visible to human eyes, it would appear dozens of times larger than the full moon, dominating our entire night sky. The halos of Andromeda and the Milky Way already intersect in space, meaning we're technically already inside Andromeda's outer reaches. This overlap represents the beginning of their merger process, the first stage of a cosmic transformation that will reshape both galaxies completely. The invisible boundaries between galaxies are already beginning to blur. Out where space seems empty, gas and dust from two massive spiral systems are starting to mix together. These atmospheres stretch far beyond what we can see with our eyes, creating bridges of matter across unimaginable distances. Around each great spiral, smaller galaxies dance in careful orbits. These companions come in different shapes and sizes, some compact and bright, others spread thin across space. The dense ones might be the leftover cores of larger galaxies that were torn apart long ago, their outer layers stripped away by gravity's relentless pull. Further out, dozens of dwarf galaxies follow their own mysterious paths through the darkness. Their movements tell us stories about invisible matter, the dark substance that outweighs everything we can see. By watching how these small galaxies move, astronomers can map the hidden scaffolding that holds entire galactic systems together. The scale of these cosmic neighborhoods defies easy understanding. A single galactic system, with all its satellites and invisible halo, can span more than 1 million light-years. That distance is so vast that light, traveling at its incredible speed, takes over 1 million years to cross from one side to the other. In our local corner of the universe, two giant spirals dominate everything else. Like binary stars locked in an eternal dance, they control the motion of every smaller galaxy nearby. The famous Magellanic Clouds, visible from Earth's southern hemisphere, orbit around this gravitational center. Even the third largest galaxy in our group follows the combined influence of these two massive systems. When we study distant galaxies, we're often looking at cosmic time machines. Their light carries information about how they appeared millions or billions of years ago. Some show signs of ancient collisions, with streams of stars stretched across space like cosmic rivers. These stellar streams are the archaeological evidence of mergers that happened long before Earth even existed. The color of a galaxy tells us about its age and activity. Younger systems blaze with blue light from hot, newly formed stars. Older ones glow with the reddish light of ancient suns, their star-forming days mostly behind them. This transition from blue to red happens slowly, over billions of years, as galaxies consume their raw materials and settle into a quieter phase of existence. For scientists trying to understand how galaxies work, having a nearby example is invaluable. Distance usually makes it impossible to study individual stars in other galaxies. They blur together into a smooth glow, their separate identities lost across space. But in our closest galactic neighbor, astronomers can pick out single stars, measure their properties, and trace their movements with remarkable precision. This proximity led to one of the most important discoveries in the history of astronomy. Nearly a century ago, astronomers identified special variable stars that pulse with predictable brightness. These cosmic lighthouses allowed them to measure distances with unprecedented accuracy. The results were shocking, proving that the universe was far larger than anyone had imagined. Today, detailed studies continue to reveal new secrets about galactic structure and evolution. Computer simulations can predict what will happen when massive systems eventually merge. The process takes billions of years, with multiple close encounters before the final union. Stars get flung into new orbits, creating spectacular tidal streams that persist long after the collision ends. Looking at a nearby spiral galaxy is like seeing our own cosmic home from the outside. We can never step back far enough to view our own galaxy's grand design, but we can study similar systems and piece together what we might look like to distant observers. Every spiral arm, every dust lane, every glowing star-forming region has its counterpart somewhere in our own stellar city. This perspective shift changes how we think about our place in space. Imagine standing on a world orbiting a distant star, looking up at a sky filled with unfamiliar constellations. From that vantage point, our entire solar system would be just one tiny point of light among hundreds of billions. The beings there, if they exist, might wonder about our worlds, just as we wonder about theirs. The concept of cosmic distance becomes almost philosophical when you consider different scales of measurement. What seems impossibly far from a human perspective is practically next door in cosmic terms. The universe spans nearly 100 billion light-years, making our local neighborhood seem almost cramped by comparison. Light itself becomes a messenger across these vast spaces, carrying information from one world to another. The photons reaching our telescopes tonight began their journey before human civilization existed. Yet in the grand timeline of the universe, the travel time is just a brief moment. This creates a strange intimacy across the void, connecting distant worlds through the simple act of starlight touching our instruments. Our cosmic neighborhood operates like a small town compared to the bustling metropolises found elsewhere in the universe. In rich galaxy clusters, hundreds or thousands of systems crowd together in spaces not much larger than our local group. There, collisions happen frequently, and the largest galaxies grow into true monsters by consuming their neighbors. The gravitational environment in these dense regions is far more chaotic than our relatively peaceful corner of space. Galaxies there experience constant harassment from their neighbors, with gas stripped away and star formation triggered by close encounters. The largest cluster galaxies can contain trillions of stars, dwarfing even the most massive spirals. By contrast, our upcoming merger will be a gentler affair, a slow gravitational waltz that unfolds over billions of years. The process has already begun at the outermost edges, where invisible matter and tenuous gas clouds are starting to interact. This cosmic collision will reshape both galaxies, but it's happening so slowly that civilizations could rise and fall countless times before the final act concludes. When we think about galaxies meeting in space, we might picture some kind of cosmic car crash, but the reality is far more graceful than that. These aren't solid objects smashing into each other. They're more like vast collections of points of light, with enormous empty spaces in between. The distances between individual stars are so immense that when galaxies encounter each other, the stars themselves rarely come close to touching. What happens instead is a slow, elegant dance that unfolds over billions of years. Gravity reaches across the void, gently tugging and reshaping these island universes. The orderly spiral arms begin to stretch and warp. Stars get pulled into long streams that arc through space like cosmic ribbons. It's choreography on the grandest scale imaginable. The process starts when two galaxies first begin to feel each other's gravitational pull. Their outer halos overlap first, and the faint stars on the edges start to shift their paths ever so slightly. As the cores draw closer, tidal forces grow stronger. Arms twist, symmetry unravels, and delicate bridges of stars form between the two systems. Gas clouds within the galaxies behave differently than the stars. While stars mostly glide past each other untouched, gas actually collides directly. When it does, it compresses and heats up, triggering spectacular bursts of new star formation. These stellar nurseries can create hundreds of new suns each year, far more than a typical quiet galaxy produces. The light from these newborn star clusters makes merging galaxies some of the brightest beacons in the universe. For a few 100 million years, they blaze with incredible intensity, then gradually settle down as the gas gets used up or blown away by stellar winds and supernovas. About 60 million light-years from us, in the constellation Corvus, we can see this process happening right now. The antenna galaxies are two spiral systems roughly the size of our own Milky Way, locked in the midst of merging. Long tidal tails stretch outward from their centers, giving them the appearance of delicate insect antennae. In the region where they overlap, infrared telescopes reveal hundreds of bright knots where stars are forming at incredible rates. The Whirlpool Galaxy offers another fascinating example. Its smaller companion has passed through the larger disk, creating density waves that have actually sharpened the spiral arms and fueled new star formation along them. Sometimes these encounters enhance a galaxy's structure before eventually transforming it completely. This process of galactic merger is one of the fundamental ways the universe evolves. Every galaxy we see has absorbed others at some point in its history. Our own Milky Way bears the scars of past collisions, faint streams of stars in its outer regions that are remnants of smaller galaxies it has consumed over billions of years. The motion of stars changes dramatically during these encounters. Before a merger, most stars follow neat, orderly orbits around their galaxy's center. As two systems draw near and their gravitational fields overlap, those orbits become chaotic. Some stars get flung outward into those long tails we see, while others fall inward toward the center. The organized rotation gradually converts into random motion. Over time, this process usually erases the distinctive disk structure of spiral galaxies entirely. The end result is typically an elliptical galaxy, a smooth, featureless ball of stars with little rotation and very little gas left over. It's a kind of cosmic aging process, where the dynamic spiral structure of youth gives way to the settled elliptical form of maturity. The shapes that emerge during these interactions are among the most beautiful and complex structures in the universe. The tadpole galaxy stretches out a tail, nearly 300,000 light-years long, formed by stars pulled away during a collision. The mice galaxy show twin trails curving gracefully outward, the result of their gravitational dance frozen in a moment we can observe. Computer simulations now allow astronomers to recreate these events in remarkable detail. By modeling the masses, velocities and gas content of two galaxies, scientists can watch how the entire interaction unfolds over billions of simulated years. The results often match what we see in real telescope images, confirming our understanding of how gravity works on these vast scales. What's particularly striking is that despite the dramatic nature of these collisions, individual solar systems remain largely unaffected. The distances between stars are so enormous that direct stellar collisions are virtually impossible. Our Sun, for example, will likely survive the future merger between the Milky Way and the Andromeda Galaxy, completely intact, though its orbit will certainly change. After that merger, our solar system may find itself in a completely different part of the combined galaxy, perhaps farther from the center, perhaps closer. The night sky would be transformed, filled with new patterns of stars, but the sun would continue shining just as it does now. If Earth still exists billions of years from now, it would orbit quietly amid this shifting sea of light. These galactic encounters play an essential role in spreading the chemical elements necessary for planets and life. When gas clouds crash together and new stars are born in the chaos, supernovas soon follow. Those stellar explosions enrich the surrounding space with heavy elements, carbon, oxygen, nitrogen, iron, which then become incorporated into new generations of stars and planets. In this sense, collisions are engines of cosmic renewal. They redistribute material, mix it up, and restart cycles of creation that might otherwise fade away. Without these interactions, the universe would be a much more static and ultimately less interesting place. The merger we're headed for with Andromeda will likely follow the same pattern we see in other galactic collisions. The first close encounter will distort both galaxies, triggering new waves of star formation. Subsequent passes will bring the cores closer together, with their central black holes beginning a slow inward spiral that will take billions of years to complete. Eventually, they'll settle into a single, larger galaxy glowing quietly in the darkness. Astronomers predict this final system will be an elliptical several 100,000 light-years across, containing perhaps twice the number of stars as either original galaxy possessed. In the far future, when cosmic expansion has carried other galaxies beyond our observable horizon, this merged system may be all that remains visible. The night sky of that distant epoch will contain only the stars of our own galaxy. The rest of the universe will have faded from view, carried away faster than light itself by the acceleration of expanding space. Yet even that seemingly permanent state is only temporary on cosmic timescales. Over trillions of years, star formation will eventually cease as gas runs out. The remaining stars will burn through their fuel and fade into darkness. The central black hole will continue growing as it absorbs what little material remains. Eventually, the galaxy will dim completely, its light dispersing, its energy spent. What began as a bright collision of two spirals will end as a quiet, dark remnant drifting through an empty void. Every galaxy in the universe shares this ultimate fate, though it lies so far in the future that it's almost beyond imagination. Still, in the present era, collisions represent signs of life, of movement, of ongoing change. They demonstrate that our universe is not static or finished, but continues to evolve and grow more complex. Every time two galaxies meet, new stars ignite, new structures form, new patterns emerge across the cosmic web. The universe breathes through these encounters, expanding and evolving in ways that are simultaneously vast beyond comprehension and delicate in their intricate beauty. Perhaps there's something profound in contemplating how destruction and creation are so intimately linked on these grandest of scales, how the apparent violence of collision gives birth to the most spectacular displays of cosmic artistry we can observe. When you peer into the depths of space, everywhere you look, cosmic collisions unfold before your eyes. Some galaxies stretch and warp, their shapes twisted by gravitational encounters that happened millions of years ago. Others trail long streams of stars behind them, like cosmic breadcrumbs marking their path through space. These distorted shapes tell stories of violence and creation happening on scales we can barely comprehend. Ring galaxies form when smaller companions punch straight through larger ones, leaving ripples in stellar neighborhoods. Each twisted spiral, each elongated arm, captures a moment in a dance that will continue long after our sun burns out. It's tempting to think these collisions are rare events, given how empty space appears. But in the grand theater of the universe, they're actually inevitable. Gravity never sleeps, never stops pulling. What starts as tiny variations in density grows over billions of years into the complex web of galaxies we see today. The universe began almost perfectly smooth, just gentle ripples in an ocean of hydrogen and helium. But those tiny differences were enough. Gravity amplified them, creating clumps that grew into the first stars, then galaxies, then clusters of galaxies stretching across hundreds of millions of light-years. Every collision reshapes the participants in ways that seem destructive but are actually creative. Without these cosmic crashes, galaxies would stay small and quiet, their gas reserves untouched, their star formation sluggish. The incredible variety of galaxy types we observe, from elegant spirals to massive ellipticals, exists because of billions of years of mergers and interactions. Those serene, featureless elliptical galaxies weren't always so calm. They're the products of ancient spiral galaxies that collided and merged. Their orderly rotation scrambled into random stellar orbits. Their smooth glow represents the aftermath of chaos, gravity's way of finding peace after violence. Picture a time-lapse movie of the entire universe, compressed into a few minutes. Galaxies would flicker and merge like raindrops on glass, small ones clustering together, growing into giants. Spiral arms would stretch and dissolve. Streams of stars would arc across the void, everything in constant motion, yet following predictable laws. This process reveals something profound about cosmic order. Despite the apparent chaos of collisions, every outcome follows the same physical rules. Gravity, energy, and time work together with mathematical precision, creating beauty from disorder across scales that dwarf human imagination. Beyond our local neighborhood, we encounter galaxies that make our Milky Way seem modest. The familiar scale of 100,000 light-years across, a few 100 billion stars arranged in graceful spiral arms, becomes inadequate to describe what lies in the universe's most crowded regions. At the hearts of massive galaxy clusters sit giants that stretch the very limits of what gravity can hold together. These behemoths, called giant ellipticals or brightest cluster galaxies, can span over 1 million light-years. Their star counts reach into the hundreds of trillions masses, exceeding our entire galaxy by factors of hundreds. From a distance, they appear as smooth, oval glows fading gradually into darkness. No spiral arms, no dust lanes, no sharp edges, just luminous clouds of ancient starlight. Their stars move in every direction at once, creating stability through randomness, a kind of controlled chaos that's maintained for billions of years. These monsters grow through cannibalism, devouring smaller galaxies that venture too close. In the dense cores of galaxy clusters, where hundreds of systems crowd together, mergers happen constantly. Each encounter adds more stars, more mass, more complexity to the central giant. Over cosmic time, the cluster's smaller members get absorbed, their individual identities erased, but their stars preserved in the collective glow. Faint shells and streams around these giants mark the graves of consumed galaxies, ghostly reminders of cosmic meals from the distant past. Consider IC 1101, located about 1 billion light-years away in a massive cluster. This galaxy represents one of the largest known structures in the observable universe. Its diameter stretches roughly 6 million light-years, containing approximately 100 trillion stars. That number defies comprehension. If you counted 1 star per second without stopping, it would take over 3 million years to finish. Yet all of these suns exist within a single gravitational system, their combined light carrying messages from an era when Earth's most complex life forms were simple ocean creatures. The light we see from IC 1101 began its journey when our planet was barely recognizable. Since then, entire evolutionary epochs have unfolded on Earth while that ancient light traveled through space, carrying within it the record of a stellar civilization too vast to properly imagine. Up close, such a galaxy wouldn't resemble a flat disk, but rather an enormous diffuse sphere. Its outer regions fade so gradually they blend into the background darkness. The core, however, would blaze with concentrated starlight from countless suns, packed into a volume thousands of light-years wide. Unlike spiral galaxies with their orderly rotation, stars in giant ellipticals follow individual paths through space. No coordinated motion, no shared direction, just millions of separate orbits creating collective stability. Each star weaves between its neighbors without collision, a billion-year ballet of gravitational precision. At the center of these giants lurk supermassive black holes, far larger than those in ordinary galaxies. IC 1101 central black hole contains tens of billions of solar masses, a gravitational monster that once fed voraciously on surrounding matter. When such black holes actively consume gas, they release energy that can outshine entire galaxies, creating what astronomers call quasars. These beacons shine across cosmic distances, announcing the presence of growing giants. Today, IC 1101 has quieted, its black hole mostly dormant, marked only by faint X-ray emissions from its gravitational influence. Other massive systems tell similar stories throughout the universe. In the Coma cluster, roughly 320 million light-years away, 2 giant ellipticals dominate the central region. Each spans several 100,000 light-years and contains trillions of stars. Their combined gravity holds hundreds of smaller galaxies in orbit, creating a cosmic city with these giants as central skyscrapers. Between them drifts a population of refugee galaxies, survivors of earlier mergers that now orbit the cluster's gravitational core. In such crowded environments, the boundaries between individual galaxies become fuzzy. The space between larger systems fills with intra-cluster light, stars stripped from their homes during close encounters. This ghostly glow wraps around the central giants like luminous fog, difficult to detect, but crucial to understanding how these systems evolve. The formation of cosmic giants continues today, though slowly by human standards. Smaller galaxies still fall into cluster cores, adding their stellar populations to the growing central mass. Over billions of years, gravity steadily concentrates more matter into these gravitational wells. This process reveals the universe's tendency toward complexity through simplification. Individual galaxies lose their identities, but contribute to larger, more massive structures. Chaos on small scales creates order. On larger ones, spiral patterns, giving way to smooth elliptical forms, random stellar motions producing stable configurations. In contemplating these giants, we glimpse the universe's long-term fate. Gravity never stops working, always pulling, always gathering. What began as gentle density fluctuations in the cosmic microwave background has grown into structures that span appreciable fractions of the observable universe. Each giant elliptical represents billions of years of cosmic evolution, countless stellar generations, and the accumulated history of entire galactic neighborhoods. They stand as monuments to the patient work of gravity and time, reminding us that even in a universe of constant change, some processes unfold with inexorable consistency across scales that humble human imagination. The distant future holds a rather strange vision for our universe. Galaxy clusters will gradually thin out as their members get pulled into central giants. What we're left with are single enormous elliptical galaxies, the end result of countless cosmic collisions over billions of years. These galactic monsters glow with an almost nostalgic light. Their stars are mostly ancient, red and yellow suns that have been burning steadily for aeons. The raw materials for making new stars, well, they're long gone, either consumed in spectacular bursts of star formation ages ago, or blown away by powerful stellar winds. It's like looking at a city where all the construction has stopped, where everything that could be built has been built. The light from these galaxies carries a warmth to it, a steady glow that comes from generations upon generations of stellar evolution. Think of it as the accumulated wisdom of cosmic time, made visible. There's something profoundly peaceful about that thought, that all the chaos and violence of galactic mergers eventually settles into this quiet, mature state. But calling them quiet doesn't mean they're empty. Far from it. Deep in their cores, something almost unimaginable is happening. Stars pack together so densely that the night sky from any planet there would never truly go dark. Even during what we might call daytime, thousands of stars would remain visible, creating a golden haze that blurs the line between day and night. Near the central black hole, gravity becomes so intense that stars whip around at thousands of kilometers per second. The energy released from this cosmic dance heats surrounding gas to tens of millions of degrees. This creates halos of X-rays that stretch for hundreds of thousands of light years, invisible to our eyes but blazing in X-ray telescopes. These X-ray halos don't just stay put around individual galaxies. They fill the entire space between cluster members, like a hot, glowing fog that permeates everything. It's evidence of the enormous gravitational potential holding these cosmic cities together. The Coma Cluster shows us exactly this phenomenon, a vast region where multiple giant galaxies sit embedded in this superhot X-ray emitting medium. From our perspective here in the Milky Way, galaxies like IC 1101 represent something both inspiring and humbling. They show us the extreme end of what the universe can construct using nothing more than gravity and time. The same physical laws that shape our own galaxy also created these monsters. It's just a matter of scale and patience. Given enough raw material and enough cosmic time, gravity will inevitably gather everything into larger and larger structures. The process smooths out complexity, leaving behind only the most massive, most stable configurations. These colossal ellipticals are gravity's final masterpiece, in a sense. Their influence extends far beyond their impressive size. As the most massive objects in their clusters, they act like cosmic anchors. Everything else, smaller galaxies, gas clouds, even dark matter, responds to their gravitational pull. They're the conductors of a vast, slow orchestra of cosmic motion. They also control the flow of gas throughout their entire cluster. The outflows from their central black holes can prevent gas from cooling down enough to form new stars. Essentially, they shut down star formation not just in themselves, but across their entire neighborhood. It's a kind of cosmic birth control, operated on the largest scales we can imagine. When astronomers study these systems, they uncover something mysterious. The stars we can see account for only a tiny fraction of their total mass. The rest is dark matter, invisible except for its gravitational effects. By watching how galaxies move within clusters and observing how light from distant objects bends as it passes through them, scientists can map this hidden component. What they find is remarkable. The dark matter halos of these giant galaxies extend far beyond their visible edges, blending seamlessly into the dark matter structure of the entire cluster. It's as if the bright galaxy we see is just the luminous center of a much larger, invisible architecture. The very existence of these cosmic giants tells us something important about the timeline of our universe. They couldn't have formed in the early cosmos. There simply wasn't enough time for all those mergers to occur. Their presence today, massive and ancient, represents billions of years of gradual accumulation. Each one is essentially a fossil record of cosmic history. By studying their stellar populations and measuring how they move, astronomers can trace the story of how matter organized itself from the Big Bang to the present day. The stars in their cores are like archaeological artifacts, preserving information about conditions that existed billions of years ago. Trying to imagine what it would be like to live in one of these systems stretches our minds to their limits. Their cores can contain hundreds of billions of stars packed into just a few thousand light-years. For comparison, the light from their outer edges takes millions of years to reach their centers. If you somehow found yourself on a planet in one of those dense cores, the concept of darkness would become meaningless. The continuous twilight of starlight would bathe everything in that golden haze. Night and day would blur into one eternal illumination. It's a beautiful thought in a way, this idea of perpetual starlight, though it makes you wonder what kinds of life might evolve under such conditions. Despite their incredible mass and energy, these galaxies possess an almost meditative calm. They rotate slowly, their stellar motions largely random and self-canceling. The fuel for dramatic new star formation is exhausted. What we see now is the glow of endurance, old stars continuing their long burn, long after their most active and creative years have passed. There's something deeply philosophical about that transition from chaos to calm, from creation to preservation. These galaxies have reached a kind of cosmic maturity, a state of being rather than becoming. Where our Milky Way still spins actively and creates new stars, these giants have settled into a more permanent existence. In telescope images, they don't always immediately grab your attention. Their light spreads out softly, their boundaries fade gradually into space. You only begin to appreciate their dominance when you notice how far their glow extends, how many smaller galaxies orbit them like cosmic moons, how their presence fills and defines the center of their cluster, those faint smudges scattered around them in photographs. Each one represents a survivor of past gravitational encounters. Some are galaxies that managed to avoid being completely consumed, at least for now. The entire cluster becomes their domain, a metropolis of galaxies held together by their overwhelming gravity. If we think of the Milky Way as an island in space, these giant ellipticals are more like continents. They gather everything in their vicinity, slowly incorporating it into themselves until little remains but their own ancient light. This process will continue, though at an ever-decreasing rate as cosmic expansion carries distant galaxies beyond their reach. Eventually, these giants will stand alone, each surrounded by the ghostly remnants of their former companions, drifting through an increasingly empty cosmos. Their existence offers us a preview of the universe's eventual fate. As expansion accelerates, distant galaxies will recede beyond the edge of visibility. Only gravitationally bound clusters like these will remain intact, isolated islands of matter in an ocean of expanding space. Within each cluster, the central giant will shine as the last great structure, the ultimate achievement of gravity's patient work. In that far future, when most galaxies have merged and most stars have dimmed, these colossal systems will serve as the final lighthouses, immense, ancient, and utterly alone. For now, though, they function as markers of cosmic possibility. They demonstrate how large a galaxy can grow, how far matter can gather under its own gravitational influence. They remind us that our own Milky Way, impressive as it seems to us, represents just one point on a vast continuum that stretches from the tiniest dwarf galaxies to these cosmic behemoths. And while the Milky Way will never reach their scale, its own destiny, merging with Andromeda and then absorbing smaller companions over billions of years, follows the same basic script. It's the same story of gravitational gathering, just written in smaller letters across a shorter span of cosmic time. Galaxy clusters operate like vast metropolitan areas scattered throughout the cosmos. Gravity acts as the binding force, pulling hundreds, sometimes thousands of galaxies together into these enormous structures. The comparison to cities isn't purely metaphorical. These clusters actually function as cosmic neighborhoods where galaxies interact, merge, and evolve together over billions of years. At the heart of nearly every major cluster sits a dominant galaxy. Much like a capital city anchors a region, these central giants dwarf everything around them, having grown to their impressive sizes through countless mergers with smaller neighbors. The process resembles urban growth, where smaller communities gradually get absorbed into expanding metropolitan areas. IC 1101 stands as perhaps the most spectacular example of this cosmic urbanism. Located in the Abell 2029 cluster, roughly 1 billion light-years from Earth, this galaxy stretches across 6 million light-years. To put that in perspective, you could fit 60 Milky Way galaxies side by side within IC 1101's diameter. The scale becomes even more staggering when you consider its stellar population, somewhere around 100 trillion stars, though precise counts become meaningless at such magnitudes. The light we observe from IC 1101 began its journey when Earth was still in its infancy, populated only by simple multicellular organisms in ancient oceans. This creates an interesting temporal paradox. We're essentially viewing a snapshot of the universe's adolescence while living in its middle age. The galaxy we see today has undoubtedly continued evolving, but that information won't reach us for another billion years. These massive central galaxies don't simply appear fully formed. Their construction spans cosmic epochs, built through a process astronomers call hierarchical assembly. Smaller galaxies, drawn together by gravity, gradually spiral inward toward the cluster center. Each collision adds mass, stars, and complexity to the growing central body. It's cosmic recycling on the grandest possible scale. The environment within IC 1101 would be utterly alien to our experience. Near the core, stars packed together thousands of times more densely than in our solar neighborhood. The night sky would never truly darken, filled instead with the collective glow of countless nearby suns. Moving outward from this brilliant center, star density gradually decreases, but the galaxy's influence extends far beyond any traditional boundary. Central to IC 1101's structure lurks a supermassive black hole weighing approximately 40 billion times our sun's mass. This cosmic behemoth dwarfs the black hole at our galaxy's center by a factor of 10,000. Such extreme objects likely grew alongside their host galaxies, fed by infalling matter and mergers with other black holes. During their active phases billions of years ago, these giants probably blazed as quasars, among the brightest objects in the early universe. Other clusters host their own central giants, each with unique characteristics. The Perseus cluster features NGC 1275, a galaxy that continues actively forming stars and blazes brightly in radio wavelengths. The Coma cluster contains two massive galaxies, NGC 4874 and NGC 4889, that share dominance over their cosmic neighborhood. In our local region, The Virgo cluster is ruled by M87, famous for being the first galaxy whose central black hole was directly imaged. These cosmic cities exist within vast ecosystems of hot plasma. The space between galaxies isn't empty. It's filled with gas heated to tens of millions of degrees. This creates an invisible ocean through which galaxies swim, their motion stripping away outer gas layers and gradually quenching star formation. Over time, many cluster galaxies become satellites of the central giant, their individual identities slowly absorbed into the larger structure. The colors of these ancient galaxies tell stories of their age. Most appear golden rather than blue, indicating their stellar populations consist primarily of older, cooler stars. The rapid star formation that once characterized their youth has largely ceased. They've become cosmic elders, stable and enduring, having consumed most available material for creating new stars. Observing these structures raises profound questions about growth, time, and cosmic destiny. Every massive galaxy represents the accumulated history of countless smaller predecessors. Their smooth, featureless appearance results from thorough mixing during numerous mergers. Each collision erased individual galactic characteristics, creating something new from the combined remnants. The timescales involved challenge human comprehension. These galaxies required billions of years to reach their current sizes, growing through processes so gradual they're essentially invisible within human lifespans. Yet the end result demonstrates how patient, persistent forces can create structures of unimaginable complexity and beauty. Perhaps most remarkably, this same assembly process continues today. Smaller galaxies still fall into clusters, central giants still grow through mergers, and new cosmic cities still form in the universe's largest gravitational wells. We're witnessing not just ancient history, but ongoing cosmic evolution that will continue long after our own solar system has faded away. The study of these galactic metropolises reveals something profound about accumulation and persistence. In a universe governed by entropy and decay, gravity creates pockets of increasing organization and complexity. These cosmic cities represent triumph over cosmic expansion, regions where matter has successfully gathered and concentrated despite the universe's overall tendency toward dispersion. In the universe's most crowded neighborhoods, something remarkable happens. The density of early cosmic regions determined everything. Where matter clustered tightly together, massive galaxies grew at incredible speeds. In the lonelier parts of space, where galaxies barely exist, nothing like these giants ever formed. These cosmic metropolises emerged from the universe's richest breeding grounds. Think of them as the Manhattan districts of deep space. Every galaxy in a cluster resembles a skyscraper, individual yet connected to something much larger. The gaps between them stretch like air between buildings, enormous to us, but still part of one unified structure. At the heart sits the central giant, a cosmic capital. Ancient, massive, weathered by time. Smaller, younger galaxies orbit around it like suburban developments, circling a downtown core. Light travels between them the way traffic flows through city streets, covering distances that seem eternal to us, that to gravity feel like nothing more than background noise. These enormous cosmic cities keep reshaping everything around them. Their gravity bends light from even more distant galaxies, twisting it into perfect arcs and rings. Astronomers call this gravitational lensing. It lets us see objects that would otherwise be too dim to detect. Through these natural lenses, we peer deeper into the past itself. We glimpse galaxies that formed when the universe was just a baby, a tiny fraction of its current age. These great cosmic cities work as both destinations and windows, their gravity revealing secrets that lie far beyond. From our position in the Milky Way, these clusters look like faint smudges through telescopes. Sometimes they appear as scattered collections of points. The Virgo cluster sits as our nearest major neighbor, roughly 50 million light-years away. It contains several thousand galaxies packed together. If you could somehow see the entire Virgo cluster at once, its central region would be ruled by a galaxy called M87, surrounded by its halo of companion galaxies. Further out, spiral galaxies, like M100 and M99 spin gracefully, their elegant shapes still perfectly intact. Beyond Virgo lies the Coma cluster, marking another incredibly dense region. Even further out, stretching between these massive hubs, are filaments of galaxies that reach across space like connective tissue. Together, they form what astronomers call the cosmic web. The clusters serve as nodes, bright intersections in this vast network. Calling them cities goes beyond simple metaphor. They have complex hierarchies, rich histories, constant interactions. They grow through trading gas, stars, and gravitational influence. They expand until they can no longer pull in new members. Then they settle down, their boundaries defined by the universe's own expansion. Inside them, smaller galaxies orbit like satellites around a planet. Within those galaxies, planets circle their stars. The same pattern repeats from the largest scales down to the smallest ones. It's like a fractal made of motion, held together by one simple universal force. If you could somehow drift through one of these clusters, light would surround you everywhere. Faint, distant, overlapping beams from countless sources. Galaxies would float in every possible direction. Some appear round and red, others glow faintly blue. Their shapes get distorted by motion and incredible distance. The central giant would shine like a sunrise that never ends, its light scattered through millions of light years of dust and gas. Space would feel crowded and endless at the same time. Every direction would hold infinite depth. Every tiny speck of light represents a collection of entire worlds. In that endless glowing stillness, you might start to feel something that astronomers sometimes mention but rarely discuss in detail, a sense of scale that stops feeling measurable and starts feeling continuous instead. The same gravity holding your feet to the ground right now is identical to the force that built these galactic giants. The same physical laws governing planetary motion also control how entire galaxies merge together. There's no real dividing line between the ordinary and the colossal. The universe operates the same way everywhere, just on wildly different scales. These cosmic monuments represent billions of years of steady, patient accumulation. They prove that incredible complexity can emerge without chaos taking over. Order can arise from gravity alone. They remind us that the universe has existed long enough to construct things larger than human imagination can grasp, yet it remains simple enough to be understood, using the same physics we use to measure an apple dropping from a tree branch. These galactic clusters contain their own internal weather systems. Hot gas flows between galaxies, like wind, between buildings. Sometimes galaxies collide and merge, their shapes stretching and distorting over millions of years. The process looks violent from our perspective, but to the universe, it unfolds as slowly as mountains rising on Earth. Dark matter plays a crucial role in these cosmic cities, even though we can't see it directly. It forms invisible scaffolding that holds everything together. Regular matter, the stuff we can observe, makes up only a small fraction of each cluster's total mass. The rest remains hidden, detectable only through its gravitational effects. As we drift away from these dense cluster cores in our imagination, we enter the spaces between them. Out there lie the cosmic voids, regions where galaxies become incredibly rare. Light grows scarce, and empty distances stretch unbroken for hundreds of millions of light years. Even those seemingly empty regions play essential roles in the universe's grand architecture. The clusters and voids work together, creating a delicate balance between presence and absence, between the crowded and the desolate. At some point, when we try to grasp just how big the universe really is, our brains simply give up. We can handle a light year, which is about 9 trillion kilometers, the distance light travels in one Earth year. We can even manage to think about our galaxy being 100,000 light years across. But when we step back further, when we try to imagine the true architecture of everything that exists, something strange happens to our minds. The numbers become just sounds we make, words we can say but never really feel. And yet, this is where the real universe lives. In scales so vast that even light, moving at the fastest speed possible, takes billions of years to cross them. Think about this for a moment. Light itself becomes slow at these distances. The most distant galaxies we can see sent their light toward us when the universe was less than 1 billion years old. That light has been traveling through expanding space ever since, its wavelength stretched, its energy thinned, but still it arrives. When we look at those faint smudges through our telescopes, we're not seeing galaxies as they are now, we're seeing history itself captured in living light. Our galaxy sits inside something called the Laniakea supercluster. This structure spans more than 500 million light-years and contains about 100,000 galaxies, all moving along curved paths determined by gravity. They're all flowing towards something astronomers call the Great Attractor, a gravitational center that pulls on everything around it. The volume of Laniakea alone is staggering. Light would need 500 million years to travel from one end to the other. If you could send a beam of light across it today, it would still be traveling when entire geological ages had passed on Earth. The light would not reach the other side until life had evolved from simple organisms into complex creatures. Yet even this supercluster is just a small piece of something much larger. When astronomers started mapping galaxies on truly enormous scales, they discovered something unexpected. Galaxies aren't scattered randomly through space. Instead, they form a web, an intricate network of filaments and vast empty regions called voids. The pattern looks almost biological, like neural tissue or the branching of blood vessels. Galaxies gather along these filaments, connected by threads of dark matter that span hundreds of millions of light-years. Where the filaments intersect, massive clusters form, dense knots of galaxies bound together by gravity. Between the filaments lie enormous voids, some stretching 300 million light-years across, regions almost completely empty of galaxies. This cosmic web wasn't always there. In the first few 100,000 years after the Big Bang, the universe was nearly uniform, a hot, dense soup of matter and radiation. The differences in density were incredibly small, just tiny fluctuations you can still see today in the cosmic microwave background. But over billions of years, gravity amplified those small differences. Regions that were slightly denser pulled in more matter, growing denser still, while emptier regions lost matter and became voids. The result is the universe we observe today, a vast web where galaxies trace the bright patterns of ancient ripples in the early cosmos. The observable universe, the portion from which light has had time to reach us since the Big Bang, has a diameter of roughly 93 billion light-years. That number isn't just a distance, it's an expanse so large that human language was never designed to handle it. Every galaxy, every cluster, every supercluster we've ever observed exists inside that sphere. Recent estimates suggest the observable universe contains around 2 trillion galaxies. Each galaxy holds hundreds of billions of stars. Each star, on average, hosts at least one planet. This means the observable universe could contain more worlds than there are grains of sand on every beach on Earth. To make these scales more approachable, astronomers use analogies. If the Milky Way were the size of a dinner plate, Andromeda would be another plate 2 feet away. The entire local group would fit inside a small room. The Virgo cluster would fill a large city. Laniakea would span continents, and the observable universe would be the size of Earth itself. But even these analogies fall short, because they assume physical scales we can hold in our minds. The true challenge isn't that the universe is large, it's that it's continuous. Every part connects to every other part, through time, through gravity, through the shared expansion of space. The same physics that shapes an atom's orbit shapes a galaxy's rotation. The same principles that govern sunlight govern the evolution of the entire cosmos. On incomprehensible scales, everything that exists shares one origin and one fate. The universe's expansion means that distant galaxies move away from us faster the farther they are. This relationship defines the Hubble constant, which measures the rate of expansion. When we observe extremely distant galaxies, we see their light stretched by expansion, redshifted into longer wavelength. The most distant galaxies have redshifts so high that their light has been stretched more than tenfold. This tells us the universe has expanded more than 10 times since that light was emitted. At these scales, even light becomes a slow traveler, crossing expanding space as the cosmos grows around it. Space and time are not separate in cosmology, they're part of the same continuum. The farther we look, the older the light becomes, and the older the light, the farther the source has receded. The universe grows while we observe it. Scale is not constant. Even apparently empty space contains extraordinary things. A single cubic meter of intergalactic space holds only a few atoms on average. But it also contains dark matter and dark energy, invisible components that make up the vast majority of everything. Ordinary matter, the stuff that forms stars, planets, and people, comprises less than 5% of the universe. Dark matter provides the scaffolding for galaxies and clusters. Dark energy drives the expansion of space itself. When we talk about scale, we're describing not just distance, but the structure of everything that fills that distance, both visible and invisible. This incomprehensible scale has a strange effect on our sense of significance. On one hand, it makes us seem impossibly small, a species living on a thin crust of rock, orbiting an average star in an ordinary galaxy. On the other hand, it places us within something vast, continuous, and governed by universal laws. We are not separate from this immensity, we are part of it. Our smallness doesn't remove us from the universe's story, it locates us within it. The atoms in our bodies were forged in stars. The energy that powers our cells is the same energy that fills space as radiation. The carbon we exhale is older than the sun. The calcium in our bones was born in a supernova's core. We are made of the same matter that fills galaxies, arranged temporarily into patterns of awareness. The incomprehensible scale doesn't exclude us, it includes us completely. Astronomers say the universe may be unbounded, meaning it has no edge but curves back on itself like a sphere's surface. On incomprehensible scales, direction loses meaning. There is no center, no edge, no up or down. Every point is equally valid. This principle, called cosmological isotropy, means that from every galaxy, the universe looks essentially the same on large scales. From Andromeda, the cosmos would appear just as it does from the Milky Way. Every observer stands at the center of their own observable universe, surrounded by a vast sphere of light defined by time and distance. The incomprehensible scale isn't just about size, it's about unity. Everything from the smallest particle to the largest cluster participates in the same cosmic event. The distances are unfathomable, but the connection is immediate. If you could step outside the universe and look back, you wouldn't see borders or corners. You'd see something smooth and continuous, glowing faintly with the light of countless galaxies, stretching endlessly in every direction. It wouldn't be measurable, only recognizable as existence itself. Perhaps that's what makes it truly incomprehensible. Not that it's too big to imagine, but that it's too complete to separate into parts. It's everything at once. When we return our thoughts to smaller scales, back to galaxies, stars, our own planet, nothing has changed except perspective. The numbers we use are only tools for describing what can't really be contained by numbers. The incomprehensible isn't meant to be conquered by understanding, it's meant to be experienced as the natural condition of existence. Somewhere in that vast continuum, in one quiet spiral among trillions, a small species sits awake in the darkness, measuring, imagining, wondering about what it sees. That act alone of noticing, of thinking, connects the smallest mind to the largest scale. The incomprehensible becomes something you feel, not as size, but as belonging. When you picture the vast emptiness of space, it's easy to think the universe is mostly nothing, standing in deep cosmic emptiness. Darkness would stretch in every direction, broken only by the faint glow of distant galaxies. Yet something invisible works constantly around you, something that shapes everything from the tiniest star cluster to the grandest cosmic structures. This invisible sculptor never rests, never weakens, never gives up. Gravity operates like the universe's most patient architect, where other forces push and pull with dramatic flair. Gravity simply waits, accumulates, organizes. It transforms chaos into order through pure persistence. Without this quiet influence, the cosmos would hold no pattern whatsoever. No galaxies would cluster together, no stars would shine, no worlds would harbor the chemistry of life. Think of how a single massive object bends the fabric of space around itself, like a heavy marble placed on a stretched sheet. Now imagine hundreds of billions of such objects working together. Their combined influence creates profound curves in spacetime, deep wells of gravitational attraction that draw in everything nearby. The universe becomes a landscape of invisible valleys and peaks, all carved by the collective weight of matter. Galaxies behave remarkably like social creatures. They cluster together in groups that range from intimate gatherings of a few dozen members to massive assemblies containing thousands. Within these cosmic neighborhoods, each galaxy moves in a slow, eternal dance, following paths bent by their shared gravitational center. It's a delicate balance between motion and attraction, where every member plays a role in an ongoing performance directed entirely by gravity's script. On our human scale, gravity feels almost disappointingly weak. It keeps us anchored to the ground, holds planets in their orbits, creates the familiar pull we experience every day. But this apparent weakness exists only because gravity's influence gets divided among countless objects. When mass accumulates in truly impressive quantities, when the cosmic crowd grows large enough, gravity's effects multiply dramatically. Many small influences combine into something vast and enduring. The visible galaxies in these cosmic gatherings represent just a small fraction of what's actually there. Most of a cluster's mass hides in two invisible components that dwarf everything we can see. Hot gas, heated to tens of millions of degrees, fills the spaces between galaxies, glowing in X-rays that reveal its presence. Even more mysterious is the dark matter that forms enormous halos around each cluster, binding everything together with its gravitational embrace. Scientists discovered dark matter partly because galaxies in clusters move too fast to stay bound by the gravity of visible matter alone. The fact that these cosmic communities don't fly apart tells us something massive and invisible must be holding them together. Dark matter extends far beyond what telescopes can detect, forming the true skeleton upon which visible structures hang. It determines how galaxies move, how fast they orbit, how they interact with their neighbors. When light from distant galaxies passes through these massive clusters, something fascinating happens. The intense gravity bends that light's path, creating distorted images, elongated arcs, sometimes complete rings of magnified light. This gravitational lensing acts like a cosmic telescope, revealing both the presence of dark matter and galaxies too distant to see otherwise. The shapes of these light distortions map gravity's invisible landscape with remarkable precision. The crowd's influence doesn't just hold galaxies together, it actively transforms them. As galaxies move through their cluster's hot gas, they encounter something like a cosmic wind that strips away their outer material. This ram pressure stripping halts new star formation, gradually transforming spiral galaxies into smoother, more rounded shapes. The crowd reshapes its members simply by existing around them. In the densest cosmic neighborhoods, collisions become common. Galaxies passing close to one another get stretched by gravity's tidal forces, creating long streams of scattered stars. Some merge completely, building larger systems. Others get torn apart entirely, their stars scattered into the space between galaxies. Over billions of years, these interactions feed the giant galaxies that dominate cluster centers, a slow process of mass transfer from the edges inward. The most massive clusters in the universe, with names like Coma and Perseus, represent the crowded hearts of the cosmic web. They sit at the intersection points where filaments of galaxies converge, containing not just thousands of galaxies but enormous reservoirs of hot gas. Together, these components outweigh all visible stars combined, yet dark matter still comprises the majority of their total mass. Gravity possesses a unique property that sets it apart from nature's other fundamental forces. It never repels, only attracts. The more matter you gather, the stronger its pull becomes, and the stronger the pull, the more matter accumulates. This creates a feedback loop, written into the fabric of space itself, explaining why the universe appears clumped into structures rather than spread evenly throughout space. In the early universe, wherever matter gathered slightly more densely than average, gravity amplified that small advantage. Over cosmic time, those tiny excesses grew into galaxies, clusters, and the vast filaments that now form the cosmic web. It's a story of small differences becoming enormous structures through gravity's patient accumulation. Modern galaxy clusters showcase motion on almost incomprehensible scales. Individual galaxies orbit their cluster's center at speeds exceeding 1,000 kilometers per second, yet take billions of years to complete a single orbit. From our perspective, these motions appear frozen in time. But on scales of hundreds of millions of years, everything moves along predictable paths through the gravitational field created by all the others. Clusters themselves don't exist in isolation. They gather into even larger structures called superclusters, which contain thousands of galaxies and dozens of clusters flowing along dark matter filaments toward regions of higher density. Our own local cosmic neighborhood sits within the Laniakea supercluster, where we move towards something called the Great Attractor. This motion isn't random, but reflects the universe's overall architecture, where gravity organizes movement on every conceivable scale. Picture the universe as a vast invisible ocean, where every concentration of mass creates currents in space-time. Where many currents meet, they merge into larger flows that sculpt the cosmos over billions of years. The galaxies we observe are like foam on this ocean surface, tracing the motion of something far deeper and more powerful than what meets the eye. The same principles operate within individual galaxies. In the Milky Way, the combined gravity of billions of stars balances against the outward motion of rotation, creating the stability that allows spiral patterns to persist. Density waves move through the spiral arms, compressing gas clouds and triggering new star formation. Even here, individual stars act collectively to create something larger than any single component. At the largest observable scales, the cosmic web itself exists because of this collective gravitational influence. Galaxies along vast filaments move slowly toward the nodes where clusters reside, feeding them like rivers feeding a lake. This hierarchical formation continues today, with smaller structures falling into larger ones merging into greater wholes. The universe still assembles itself according to gravity's gentle but insistent guidance. Gravitational lensing provides one of the most striking demonstrations of the crowd's influence in action. When massive clusters bend light from background galaxies, they create natural telescopes that reveal objects far beyond what even our most powerful instruments could normally detect. These Einstein rings and distorted arcs represent direct evidence of how mass warps space, turning the crowd's gravity into a tool for cosmic discovery. The behavior of galaxy clusters also provides clues about the universe's ultimate fate. Gravity's collective pull works against the expansion of space, and for most of cosmic history, it succeeded in slowing that expansion. But approximately 5 billion years ago, something called dark energy began driving an acceleration that continues today. This mysterious energy permeates all space, pushing it outward in opposition to gravity's inward pull. The universe's current structure represents a delicate balance between these opposing forces. Gravity tries to pull matter together, while dark energy drives space apart. In the far future, this tension will define whatever remains. As expansion continues, clusters will become isolated islands, their gravity unable to reach beyond immediate boundaries. Distant galaxies will slip away faster than light can travel, disappearing beyond the cosmic horizon. Yet within each cluster, gravity's crowd effect will persist, binding local members together, even as the universe grows emptier around them. Their internal harmony will survive the cosmic expansion, creating islands of gravitational order in an increasingly dark and lonely cosmos. The crowd's influence may shrink in scope, but it won't disappear entirely. When you consider the full picture, galaxies, clusters, filaments, the entire cosmic web, it becomes clear that gravity functions less like a force and more like a cosmic sculptor. It doesn't act suddenly or dramatically. It simply persists across billions of years, transforming early chaos into the ordered structures we observe today. Gravity arranges, collects, stabilizes, creating the quiet rhythm that underlies everything in existence. Within this grand assembly of matter, we participate as tiny but genuine contributors. Every atom in our bodies adds its infinitesimal contribution to spacetime's curvature. Earth's gravity binds us to its surface. The Sun's gravity holds planets in orbit. Our galaxy's gravity binds its stars together, and the cosmic web connects galaxies across unimaginable distances. It forms an unbroken chain of connection, stretching from the smallest scales to the largest, where the same rule governing a falling apple also governs the motion of superclusters. So when contemplating the universe's enormity, its incomprehensible distances, its endless expansion, the silent drift of cosmic structures, it helps to remember that everything remains connected by something remarkably simple. Gravity doesn't need to announce itself dramatically. It only needs time. Given sufficient time, it gathers everything into recognizable patterns, and even when those patterns fade, the underlying influence remains constant. The crowd's gravitational effect tells the story of how everything finds its place in the cosmic order, how all things, regardless of separation, remain connected through invisible threads we can measure but never directly observe. Though we can't see these connections, we feel their presence in our world's orbit, in ocean tides, in the gentle stability of stars overhead. The cosmic crowd extends outward infinitely, and we represent one small part of its collective influence, forever bound to the largest structures in the universe through the same force that holds us to the ground beneath our feet. Light travels at roughly 300,000 kilometers every second, which sounds impossibly fast until you consider the vast distances it must cross. This speed becomes the universe's own measuring stick, connecting space and time in ways that reshape how we understand everything around us. When you glance at the moon tonight, you're actually seeing it as it appeared about 1.25 seconds ago. The sun you observe is already 8 minutes in the past by the time its light reaches your eyes. These delays stretch dramatically as we look further out. Proxima Centauri, our closest stellar neighbor, shows us light that began its journey over 4 years ago. The faintest galaxies we can detect reveal themselves as they existed more than 13 billion years in the past, long before Earth even formed. Every astronomical measurement becomes fundamentally a measurement of time rather than just distance. This creates a peculiar situation where telescopes function as time machines. The deeper we peer into space, the further back in history we travel. When astronomers study distant galaxies, they witness star formation, cosmic collisions, and galactic evolution from eras when the universe was young and chaotic. The night sky transforms into a temporal landscape where every point of light represents a different moment in cosmic history. Consider the sunlight warming your skin right now. Those photons originated in the sun's core, where hydrogen fuses into helium under tremendous pressure and heat. But their journey to the surface takes an extraordinary detour. Each photon bounces countless times through the dense plasma, getting absorbed and re-emitted repeatedly. This internal journey can last hundreds of thousands of years before the photon finally escapes the sun's surface, then races across space to Earth in just 8 minutes more. The philosophical implications are staggering. The warmth you feel today might have begun its journey when early humans first discovered fire. Time and space weave together in ways that challenge our everyday understanding of when and where things happen. There's no universal moment of now shared across the cosmos. Every location experiences its own timeline, its own version of the present. This temporal stretching becomes even more dramatic on galactic scales. The Andromeda Galaxy appears to us as it existed 2.5 million years ago, when our earliest human ancestors walked across Africa. Those incredibly faint galaxies captured in deep space photographs show us cosmic infancy, less than 1 billion years after the Big Bang occurred. We're literally surrounded by ghosts from the past, their messages still arriving long after the original events ended. Einstein's relativity adds another layer of complexity to this cosmic story. Space and time form a single fabric called spacetime, which gets warped and curved by massive objects like stars and galaxies. Light follows these curves, taking paths through a geometry that's constantly shifting and stretching. When we measure distances to far objects, we're really tracing light's journey through this warped landscape. The universe's expansion adds yet another twist. As light travels across cosmic distances, the space it moves through expands, stretching the light itself toward longer, redder wavelengths. This redshift effect allows astronomers to determine both how far away objects are and how fast the universe is growing. Every photon carries within its color a record of how much space has stretched during its journey. A galaxy's light might start as blue or white, but by the time it reaches us billions of years later, the universal expansion has shifted it toward red. By measuring this color change, scientists can calculate exactly how long the light has been traveling and how much the cosmos has expanded in that time. Each beam of light becomes a messenger, carrying precise information about cosmic motion written directly into its wavelength. The most ancient light of all surrounds us constantly. The cosmic microwave background represents the afterglow of the Big Bang itself, filling every direction with faint radiation left over from when the universe first became transparent. Before this moment, roughly 380,000 years after the beginning, matter and energy were so tightly coupled that light couldn't travel freely. When the cosmos finally cooled enough for atoms to form, light was released and has been journeying ever since. This primordial light reaches us now as microwaves, its wavelength stretched more than 1,000 times by cosmic expansion. It represents the oldest possible light we can ever observe, a direct snapshot of the universe, when it still glowed with its original heat. From that point forward, light became our only messenger from the distant cosmos. Every detail we know about stars, planets, and galaxies comes to us through electromagnetic radiation, whether it's visible light, X-rays, radio waves, or gamma rays. We've never actually seen the universe directly. We've only ever observed its light, traveling across unimaginable distances to tell us what once was. Each observation is really a form of cosmic archaeology, reading messages written in wavelengths and frequencies. Light doesn't simply exist in empty space. It travels through a medium that's constantly changing. As photons journey across the universe, they experience cosmic history firsthand. Gravity bends their paths around massive objects. They slow down, passing through gravitational wells. The expansion of space stretches their wavelengths. Every image we receive has been distorted and transformed by billions of years of cosmic evolution. Some photons never reach us at all. The expansion carries their sources away faster than light can travel, creating messages that will journey forever without ever arriving. This defines something called the cosmic horizon, a temporal boundary beyond which light hasn't had enough time to reach us since the universe began. It's not a physical wall, but a limit imposed by the relationship between light speed and cosmic age. This horizon constantly shifts. Every second, light from slightly more distant regions becomes visible for the first time, while expansion carries other regions beyond our reach forever. The observable universe grows and changes, always limited by this interplay between the speed of light and the universe's expansion rate. Different distances reveal different eras of cosmic evolution. Nearby galaxies show us the mature, structured universe of today, filled with large clusters and ancient stars. More distant objects appear younger, smaller, and bluer, caught in the act of forming their first stellar generations. The deepest observations reveal galaxies, still assembling from primordial gas, clumpy and irregular, their light reaching us from when the universe was only a few 100 million years old. Even within our own galaxy, light reveals the connection between distance and time. The Crab Nebula shows us the aftermath of a stellar explosion that Chinese astronomers recorded in 1054. Nearly 1,000 years later, we still see that same event unfolding as the explosion's light continues spreading outward, illuminating surrounding gas clouds. The supernova story continues to arrive, long after the initial flash ended. On larger scales, we observe stellar explosions in distant galaxies, that occurred billions of years ago, their light only now completing the journey to Earth. Each represent a signal from deep time, a record of a moment, preserved in traveling photons. The finite speed of light creates a universe without universal simultaneity. Events that appear simultaneously from one perspective may be separated by vast time intervals when observed from elsewhere. This gives the cosmos a layered, complex structure, where every patch of sky corresponds to a different era and stage of evolution. The cosmic web we map today is really a composite image spanning billions of years, where galaxies that appear next to each other might actually be separated by hundreds of millions of years in time. Astronomy becomes the study of time's geography, using light to chart the past and reconstruct the sequence of events that led from cosmic beginnings to the present moment. The darkness between stars isn't truly empty. It's filled with faint radiation, relic photons from the early universe, distant galactic glow, too faint to see individually, and whispers of energy from ancient stars long extinguished. Every cubic meter of space contains hundreds of these ancient photons, moving endlessly and carrying the accumulated history of everything that has ever emitted light. When you look up at the night sky, you're seeing a living archive of the past projected onto the present. Some of those stars may already be gone, their light still traveling toward us. Others are newly born, their glow just beginning to spread. The universe remembers itself through light, and every photon that has ever left a star continues forward through time, carrying its story with it. This creates a strange but comforting realization. Even when sources disappear, their light remains, traveling onward as a permanent record. Every beam represents both a record and a reading, connecting us immediately to events separated by incomprehensible distances and unimaginable timescales. We exist within a cosmos that writes its own story, not in words or sounds, but in the patient, constant flow of light across space and time. Looking out into the cosmos, we find ourselves occupying what amounts to a microscopic speck within an almost incomprehensible vastness. Our entire galaxy, the Milky Way, appears as nothing more than a single point when mapped against the cosmic web of clusters and superclusters. Within this galaxy, tucked away about halfway along one of its spiral arms, sits an unremarkable yellow star. Around this star, a small collection of planets maintains their ancient dance, and among them, one particular world has achieved something extraordinary, the exact conditions needed for life to emerge and flourish. The more we examine our cosmic address, the more remarkable it becomes, not because we occupy some special position, but because we exist at all. Our sun represents the very definition of mediocrity in stellar terms. It's neither particularly large, nor unusually small, neither exceptionally hot, nor remarkably cool. Among the hundreds of billions of stars that populate our galaxy, it sits quietly on what astronomers call the main sequence, burning hydrogen into helium with steady, reliable persistence. This ordinariness extends to our planet's orbital position as well. Earth circles the Sun at just the right distance to maintain liquid water on its surface. Move us slightly closer, and the oceans would boil away into space. Push us a bit farther out, and everything would freeze solid. This narrow band around any star, where water can exist in liquid form, defines what we call the habitable zone. It's a surprisingly thin slice of space, and we happen to sit right in the middle of it. The atmosphere that surrounds us appears substantial when we feel wind or watch clouds, but from a cosmic perspective, it's almost impossibly thin. This delicate shell of gases, held in place by gravity, creates the pressure and chemical conditions that allow life to exist. Without it, our world would be just another lifeless rock, subject to the temperature extremes and radiation that characterize most planets. Perhaps most remarkable of all, within this thin atmosphere, collections of atoms have organized themselves into patterns capable of thought, memory, and wonder. We represent the universe becoming aware of itself, matter arranged in such a way that it can contemplate its own existence and origins. The fact that we can look outward and recognize our place in the cosmos speaks to something profound about the nature of complexity and consciousness. Our planet's stability depends on a delicate interplay of factors that extend far beyond Earth itself. Jupiter, that massive gas giant in our outer solar system, acts as a gravitational guardian, sweeping up asteroids and comets that might otherwise impact our world. The Moon, our constant companion, stabilizes Earth's rotational axis, preventing dramatic climate swings that would make long-term biological evolution nearly impossible. Deep within our planet, a molten iron core generates a magnetic field that deflects the stream of charged particles constantly flowing from the Sun. Without this invisible shield, our atmosphere would gradually be stripped away, leaving us as barren as Mars. Even the tilt of our planet's axis contributes to habitability, creating seasons that distribute solar energy across the globe in patterns that support diverse forms of life. When astronomers discovered that planets exist around nearly every star in our galaxy, it initially seemed to make Earth less special. The cosmos appeared filled with worlds, suggesting that places like ours might be common. But as we've learnt more about these distant planets, we've discovered just how varied and often hostile they can be. Some orbit so close to their stars that their surfaces glow with heat. Others drift so far away that any atmosphere freezes solid. Rocky worlds, gas giants, ice balls, and strange hybrid combinations fill the galaxy, each shaped by the particular circumstances of its formation and evolution. Among all this diversity, Earth stands out not for its size or composition, but for its intricate layering of atmosphere, liquid water, and living systems. We may not be unique in the universe, but we're certainly extraordinary in our local neighborhood. Our solar system's position within the Milky Way contributes significantly to Earth's habitability. We're located in one of the galaxy's spiral arms, but crucially, we're far from the crowded, dangerous environment near the galactic center. That region teems with massive stars, frequent supernovae, and intense radiation that would make the evolution of complex life extremely difficult. Out here, some 25,000 light-years from the galactic center, space is relatively quiet and stable. The density of stars is lower, cosmic catastrophes are less frequent, and life has had billions of years to develop with minimal interference. It's a cosmic suburb, if you will, peaceful enough for the slow, patient process of evolution to unfold. Yet this stability isn't permanent. Our entire solar system orbits the center of the Milky Way, completing one full revolution every 230 million years. During this vast journey, we pass through different regions of the galaxy, sometimes encountering dense clouds of interstellar material, other times drifting through emptier space. These changes occur on timescales so long that they dwarf human history, but they do influence conditions on Earth over geological time. The solar system also oscillates up and down relative to the galactic plane, like a horse on a cosmic carousel. These motions expose us to varying levels of cosmic radiation and may correlate with long-term climate changes on our planet. The galaxy doesn't notice these small variations, but for life on Earth, they represent the slowly changing backdrop against which evolution plays out. Consider Venus, our nearest planetary neighbor toward the Sun. Despite being only slightly closer to our star than Earth, Venus has become a hellish world of crushing atmospheric pressure and temperatures hot enough to melt lead. A runaway greenhouse effect has turned it into a cautionary tale of what happens when planetary climate systems tip out of balance. Mars tells the opposite story. Once warmer and wetter, it gradually lost most of its atmosphere to space, becoming the cold, dry desert we see today. Between these two extremes sits Earth, maintaining its delicate balance through a complex interplay of geological, atmospheric, and biological processes. From the perspective of another star system, Earth would be completely invisible, lost in the glare of our Sun. Even with the most powerful telescopes, it would appear as nothing more than a pale blue dot, a single pixel of light, carrying no hint of the complexity it contains. That entire pixel encompasses every ocean, every continent, every living thing that has ever existed on our world. This perspective shift from the familiar view we have from Earth's surface to the cosmic view from interstellar distances reveals something profound about scale and significance. Everything we consider important, every human achievement, every natural wonder, exists within a space so small that it cannot be distinguished from empty space when viewed from afar. Yet this doesn't diminish our importance. It highlights how remarkable it is that such complexity can arise at all. The spacecraft Voyager 1, after completing its tour of the outer planets, turned its camera back toward Earth from the edge of the solar system. The resulting image showed our world as Carl Sagan famously described it, a pale blue dot suspended in a sunbeam. From that distance there were no visible continents, no signs of life, no indication that this tiny speck harbored billions of living creatures, and the only known example of consciousness in the universe. This image serves as a powerful reminder of our cosmic context. All of human history, every war and discovery, every love story and tragedy, exists on that almost invisible point of light. We are simultaneously infinitesimally small in cosmic terms and extraordinarily significant as the only known location where the universe has developed the ability to understand itself. The atoms that make up our bodies were forged in the cores of ancient stars billions of years ago. When those stars reached the ends of their lives and exploded as supernovae, they scattered these heavy elements throughout space. Later, as new stars and planets formed from this enriched material, some of these atoms eventually found their way into living systems on Earth. The carbon in our cells, the iron in our blood, the calcium in our bones, all of these elements have cosmic pedigrees stretching back billions of years. We are quite literally made of star stuff, temporary arrangements of matter that was once part of stellar furnaces scattered across the galaxy. This connection between ourselves and the cosmos isn't metaphorical. It's the direct result of physical processes that have been operating since the early universe. The same fundamental forces that govern the motion of galaxies also determine the behavior of atoms in our bodies. Gravity, which binds galaxy clusters together across millions of light years, also holds our feet to the ground and keeps the atmosphere in place. The electromagnetic force that powers stellar fusion also drives the chemical reactions that sustain life. We exist within the same physical framework as everything else in the universe, built from the same materials and operating according to the same rules. This unity between the cosmic and the biological suggests something profound about the nature of existence itself. The universe isn't divided into separate realms of the very large and the very small. Instead, it represents a continuous spectrum of organization, from subatomic particles to galactic superclusters, all interconnected through the same underlying physics. The study of planets around other stars has revealed the incredible diversity of possible worlds. Some planets are tidally locked to their stars, with one side permanently day and the other permanently night. Others orbit variable stars whose radiation output changes dramatically over time. Some exist in binary star systems where two suns illuminate alien skies with complex patterns of light and shadow. Among the thousands of known exoplanets, a few exist in the habitable zones of their stars, where liquid water could potentially exist. But habitability depends on far more than just distance from a star. The thickness and composition of a planet's atmosphere, the strength of its magnetic field, the stability of its orbit, and dozens of other factors all play crucial roles in determining whether a world could support life as we know it. Even on Earth, the balance that allows life to flourish isn't static. Our planet has experienced ice ages, periods of intense volcanic activity, asteroid impacts, and other dramatic changes throughout its history. The climate system represents a complex dance between the atmosphere, oceans, ice sheets, and living organisms, with feedback loops that can sometimes amplify small changes into major shifts in global conditions. Looking ahead, we know that our current situation is temporary on cosmic timescales. The sun gradually brightens as it ages, and in about 1 billion years, the increased heat will likely boil away Earth's oceans. In roughly 5 billion years, the sun will expand into a red giant star, probably engulfing the inner planets entirely. Our stable, life-supporting environment exists within a relatively narrow window of cosmic time. This impermanence doesn't make our existence less meaningful. Rather, it emphasizes how remarkable it is that we're here now, during this brief epoch when conditions allow for complexity and consciousness. We represent a temporary flowering of awareness in a universe that is mostly empty space, punctuated by occasional islands of matter and energy. The overview effect, experienced by astronauts who see Earth from space, reveals our planet as a unified system without the borders and divisions that seem so important from the surface. From orbit, Earth appears as a single, integrated entity, with weather systems, ocean currents, and the thin line of the atmosphere all working together to maintain the conditions that support life. That atmosphere, which contains all the air we breathe and all the weather we experience, is proportionally thinner than the skin on an apple. Above this narrow shell lies the vacuum of space, filled with radiation and debris, but completely unable to support life as we know it. The entire biosphere, everything from the deepest ocean trenches to the highest mountain peaks, exists within this impossibly thin layer. Our moon plays a crucial role in maintaining Earth's habitability. Its gravitational pull creates tides that mix ocean waters and may have provided the environmental conditions necessary for life to first emerge along ancient shorelines. The moon also stabilizes Earth's axial tilt, preventing the dramatic climate variations that would occur if our planet wobbled chaotically as it orbits the sun. The relationship between Earth, moon, and sun creates the rhythms that define our experience of time. Days and nights, lunar cycles, and seasonal changes all result from the gravitational and orbital dynamics of this three-body system. These cycles have remained remarkably stable throughout Earth's history, providing the steady environmental backdrop against which life has evolved and flourished. Standing beneath the night sky, we see the Milky Way as a faint band of light stretching across the darkness. This seemingly modest glow represents our view from inside one of the universe's great spiral galaxies, home to hundreds of billions of stars. We're seeing the combined light of distant suns, their radiation merged into a soft, continuous radiance that has inspired human imagination for thousands of years. Our position within the galaxy gives us a unique perspective on cosmic structure. We're far enough from the galactic center to enjoy relatively stable conditions, yet close enough to the spiral arms to see the density of stars that defines the Milky Way's shape. We exist in a region of relatively low interstellar dust, which provides us with clear views of both nearby stars and distant galaxies. The solar system travels through the galaxy at about 220 kilometers per second, completing one full orbit around the galactic center every 230 million years. This means that since the Sun formed about 4.6 billion years ago, it has completed roughly 20 trips around the galaxy. All of Earth's geological history, all of biological evolution, has occurred during this slow cosmic journey. As our solar system moves through the galaxy, it encounters different environments along the way. Sometimes, we pass through regions rich in gas and dust. Other times we drift through nearly empty space. These variations occur over millions of years and may influence long-term climate patterns on Earth through changes in cosmic ray exposure and other subtle effects. The galaxy itself rotates differentially, meaning that stars at different distances from the center orbit at different speeds. This creates the spiral arm pattern we see in many galaxies, as density waves sweep through the stellar disk like ripples on a pond. Our Sun currently lies in a minor spiral feature called the Orion arm, positioned between two major spiral arms of the Milky Way. The Saturn side. From our vantage point, we can map the galaxy's structure using radio and infrared observations that penetrate the dust clouds blocking our optical view toward the galactic center. We've discovered that the Milky Way contains a central bar of stars, spiral arms populated by young, hot stars, and an extended halo of older stars and globular clusters. The entire system is embedded in a vast sphere of dark matter that we cannot see directly, but detect through its gravitational effects. This dark matter makes up the majority of the Milky Way's mass, forming an invisible scaffolding that determines the galaxy's overall structure and dynamics. We move through this unseen material constantly, swimming in a sea of particles that interact with ordinary matter only through gravity. The fact that we're surrounded by this mysterious substance adds another layer to our cosmic context. reminding us how much about the universe remains unknown. Throughout the galaxy, new stars are being born in giant molecular clouds, while older stars reach the ends of their lives in spectacular supernova explosions. These stellar death throes scatter heavy elements throughout space, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. We exist within this ongoing cycle of stellar birth and death, part of a process that has been operating for billions of years. The Milky Way itself has grown through mergers with smaller galaxies throughout cosmic history, and this process continues today. Small satellite galaxies orbit our own, slowly being disrupted by tidal forces and incorporated into the Milky Way's outer regions. In several billion years, the much larger Andromeda galaxy will collide and merge with the Milky Way, creating a new, even larger galaxy. From our perspective inside the Milky Way, this future collision will unfold over hundreds of millions of years, gradually changing the appearance of the night sky as Andromeda grows larger and the two galaxies' spiral structures become distorted. By the time this cosmic collision reaches its climax, the Sun will likely have evolved beyond its current stable phase. But the event illustrates the dynamic nature of galactic evolution on the longest timescales. Currently, we exist during a period when the Milky Way maintains its spiral structure, when star formation continues at a steady rate, and when the galaxy's disk remains relatively stable. This represents a temporary phase in galactic evolution, a time when conditions favor the emergence and persistence of planetary systems like our own. Every element heavier than hydrogen and helium in our bodies was created inside stars through nuclear fusion, then distributed throughout space when those stars died. The oxygen we breathe, the nitrogen in our DNA, the phosphorus in our bones, all of these atoms have cosmic histories stretching back billions of years. We are not separate from the galaxy that contains us. We are made from it, shaped by its processes, and sustained by its ongoing evolution. The light from distant stars that reaches us each night began its journey years, decades, or even centuries ago, carrying information about conditions throughout our local region of the galaxy. When we look up at the night sky, we're seeing the Milky Way's past, a fossil record of stellar activity preserved in the photons that have traveled across space to reach our eyes. This connection between ourselves and the cosmic environment around us suggests a profound truth about existence. We are not observers standing outside the universe looking in, but participants embedded within cosmic processes that have been unfolding for nearly 14 billion years. And our awareness represents one way that the universe has developed the capacity to understand itself. Consciousness emerging from the same physical laws that govern stellar evolution and galactic dynamics. In this vast context, Earth's fragility becomes not a source of anxiety, but a reminder of how precious and improbable our situation truly is. Against the backdrop of cosmic emptiness, extremes of temperature and radiation, and the general hostility of space to biological processes, our small planet maintains its delicate balance, providing a haven for complexity and consciousness in an otherwise largely barren universe. The same forces that shape galaxies and drive stellar evolution also create the conditions that allow us to exist, to wonder, and to gradually understand our place in the cosmic order. We are small beyond imagination, yet significant beyond measure. Temporary arrangements of matter that have achieved the remarkable ability to contemplate the infinite.